Hi, everyone. It's 10 a.m. Eastern, so we're going to get started. This is our final day of the AI to Assist Mathematical Reasoning workshop. So welcome back if you've been watching before. Before I turn it over to our chair to kind of kick things off, I'm going to quickly run through our Q&A platform Slido again. So if you would like to submit questions to the speakers and panelists, we really encourage you to do so. It's great to have your input. So if you're watching via our registration, or if you registered next to the live stream, you should have Slido embedded there, or you can also navigate to slido.com and type in AI for Math 23. And there you can submit questions, and you can also upvote other people's questions that you find interesting and especially want answered. So we will do our best to answer as many as we can. And with that, I will turn it over to Petros.
Thank you, Sam. Good morning, everybody. I'm Petros Koumoutsakos. I'm the Herbert Vinokour Chair in Computing and Science Engineering at Harvard University, and I have the distinct pleasure of chairing this workshop, AI to Assist Mathematical Reasoning. It has been 2 amazing days with a lot of great talks and very interesting presentations and discussions. On day 1, we discussed the state of the art of using AI to assist mathematical reasoning. Then on day 2, we moved forward in time. We arrived to the present day, talking about current challenges and barriers to the use of AI for mathematical reasoning. And on the 3rd and last day of the workshop, we're going to look into the future. We're going to be discussing technical advances required to expand this initiative. And we're going to hear from people in computer science, from mathematics, and also there will be stakeholders discussing this initiative. So without any further comments, I'd like to turn it over to my colleague, Talia Ringer, who's going to take care of the first session about technical advances and computer science. Talia, over to you.
Awesome. Thank you. Good morning, everyone. If you haven't met me yet, my name is Talia. I'm the chair for this session. I'm an assistant professor at UIUC. And my work is on tools that make it easier to develop and maintain formal proofs about software systems. And the session that we're going to kick off with is this research advances in computer science. So we have 3 great speakers for this. Our first speaker is Brigitte Pientka. So Brigitte Pientka is a full professor in the School of Computer Science at McGill University and leads the Computation and Logic group. Her research interest lies in developing a theoretical and practical foundation for building and reasoning about reliable, safe software systems by combining theoretical research on the logical foundations of computer science in programming languages and verification with system building. So with that in mind, you can get started, Brigitte.
All right. Can everybody hear me? Hope so.
You're good.
Okay, great. So what I wanted to talk about is really principles of programming in proof languages to bring sort of a perspective from the programming language community to this question of mathematical reasoning and what AI can do in this domain. So let me start with maybe, with how I think about the landscape in principles of programming languages. So on the one hand, I think we rely on logical ideas from logic to understand computational phenomena in programming languages. So there's this beautiful connection, for example, between linear temporal logic, which gives rise to a type system for reactive programming, modal logic, like the modal logic S4, gives rise as a foundation for meta-programming in macros. And there's a beautiful connection between linear logic and concurrent programming, in particular processes through the idea of session types. But we usually don't just design these languages in isolation. We also want to reason about programs written in these languages. And in particular, we want to reason about the languages themselves. So why do we want to reason about languages? Well, because if we have a property that the language satisfies, then all programs written in this language will actually satisfy this property. And typically we do these kinds of proofs on paper, but over the last 20 and 25 years, more and more we have been using proof assistance. So at this heart really is this idea that we can think of programs as proofs. And this is really kind of the foundation of systems like ACTA, COG, Lean, and I put in some more domain-specific proof assistance like 12 and Beluga. Oops, my slides don't want to move. Let me see. Let me reshare my slides maybe, because right now I can't move my slides. Okay. So it's really a question of trust and reliability, in my opinion. Okay, so we know that programs go wrong. And so the question on how we can trust a program and ultimately also a proof becomes sort of more and more important as we can generate code using large language models, for example. And the people who generate this kind of code are not necessarily programmers themselves. So a key piece of the software infrastructure is the software that is a compiler itself. And we know, of course, also compilers can go wrong. Compiler bugs are very hard to fix. They're hard to find. And in fact, every program is affected and potentially at risk. And so this is a study from about 10 years ago, which showed that these bug finding tools can be very successful. And in fact, they found over 195 bugs in the GCC and LLVM C compiler. So it isn't really surprising that one of the grand challenges back in the 1970s was to verify a compiler. And that challenge was voiced by Tony Hoare. That challenge took a long time coming. Okay, it was abandoned in between. 2003 it was renewed. And in 2009, we actually have a fully verified compiler, the Concurrent compiler for C. That was done by a team led by Xavier Leroy using the COG proof assistant. And I think this was a strong testament to the value and success and power of proof assistance that we have today. But if you think about software, you have to really start with the language in which the software is implemented in. So in fact, the language itself might contain flaws right from the beginning. And so that's why we're also interested in studying sort of the language designs themselves. So a good example is Java, which was one of the first languages that had a very formal, rigorous mathematical definition about 25 years ago. And it claimed this property that it was type safe. And so what type safety means is essentially that if you have a program that is well typed, it will not go wrong during the execution. It will not access memory it hasn't allocated for, and it will ultimately not crash. And so researchers were kind of investigating this claim, and there was this beautiful paper by Sofia Drosopoulou and Susan Eisenbach, Java is type safe probably, in 1996. That was followed by a note by Vijay Sarswat that said, no, Java is not type safe. And you might think, 20 years later, we kind of know what's happening. But in fact, in 2016, there was a paper, Java and Scala's type systems are unsound, and it had a proof artifact. This artifact is actually a mechanized proof. And then it proposed a core calculus, a dot calculus, and proof type soundness. And again, this was actually mechanized in a proof assistant. And it was not only mechanized once, subsequently it was mechanized, I believe, almost 3 times. Okay. So why is it hard to get theories and implementations right, you might ask, okay? And I want to highlight that programming language proofs differ really from proofs in mathematics. And so first, I think, in programming languages, we actually often are proving the same kind of theorem. So we might prove something like type safety, bisimulation, soundness of a transformation, consistency, correctness of a particular system, and so on. But why is it hard? Well, it's hard because the language for which we establish this property is in some sense a moving target. And the languages themselves, like Rust, Java, and Scala, they can be, in fact, quite large. So if you think about mathematics, I think of it sort of like a skyscraper. Okay, so in order to add to it, you're already fairly high up, and you have mastered all these lower floors, and in the end, you build sort of the last floor on top, and you're reaching really for the sky. In programming languages, things are a little different. Okay, in some sense, the ground below where we build is a bit shaky. Okay, they're a little. It's sort of like an earthquake zone, if you like. Okay, and you need to make sure that when you build houses, they don't collapse. So maybe we don't build as high of a house, but our houses still need to be actually stable. So as John Reynolds put it, the truth of the matter is that putting languages together is a very tricky business. So if you do this on paper, it's really challenging to keep track of all the details. We often skip over details, and these difficulties increase with size. And if you use a proof assistant, in principle, this should be the answer. But in fact, there's a lot of overhead in building basic infrastructure. There's a lot of boilerplate proofs. We may get lost in technical and low-level details. It's quite time-consuming, and experience on how to set up this kind of mechanization really matters. And to make this concrete, and this is not a singular example, it's a very common experience, and it's that's been going on for the last 20 and 30 years. This is an example from a paper by Andreas Rosberg and Claudio Rosso and Derek Dreyer, where they have developed a theory of modules, and they kind of formulated this theory in the Coq proof assistant. And they said, in the end, in their paper, out of total of around 550 lemmas, approximately 400 were tedious infrastructure lemmas. That's like 70% of the proof. Okay. They keep saying also that the number of required infrastructure lemmas appears to be quadratic in the number of variable cases, the number of substitution operations, and so on. And so this gives you a very concrete sense, of what we mean by this infrastructure that is required. So what are good high-level languages that would make it easier to prove actually these kinds of properties? And the answer for me is really abstractions, right? So Barbara Lischkopf already in the 1970s formulated this as saying the motivation behind the work on very high-level languages is to ease the programming task by providing the programmer with a language containing primitives and abstractions suitable to the problem area. The programmer is then able to spend the effort in the right place. They concentrate on solving the problem, and the resulting program will be more reliable as a result. Clearly, this is a worthwhile goal. And so, in order to understand where abstractions can play in, it's maybe also important to look a little bit in the past, okay? And understand where these kinds of proof assistants we've heard about, like Lean and Coq, are in fact coming from. They really come from this idea that we can think of proofs as programs. So ACTA is based on interdisciplinary type theory developed by Martin Loeb in the 70s and then mostly in the 80s. And the calculus of construction is sort of the basis of Coq and Lean, which was proposed by Thierry Concurrent and Gérard Red. And ACTA really takes this idea of proofs as programs quite literally. You write a program, and that program constitutes a proof. While Coq and Lean really take the proof as the primary, okay, and you develop a proof, and then you can extract, in some sense, the program. But there's a lot of synergy between this idea of thinking of proofs as programs. So if you think about code generation, the notion of quoting and unquoting, the notion of macros in programming, which are very common concepts, you might think now, what does this mean to have in the setting of proofs? And it's not so obvious how to actually give a foundation for code generation that scales to something like a type theory that underlies systems like Coq and Lean. The same question you can ask about incomplete proofs. Okay, so if we are talking about incremental proof development, we need to have a notion of incomplete proofs, and we need to have a notion of incomplete programs if we want to have programs that are composable, but also that to model sort of edit actions. And the fourth example I want to give is the idea of program synthesis. If you can do program synthesis in this setting, you can actually do proof synthesis. And so in some sense, you get sort of 2 times the money. Okay, advances in programming languages can be applied to the domain of proofs, and the domain of proofs leads to advances in the domain of programs. And we've seen these kind of domains growing together more and more. And so I think while tools in engineering are very important, I think a lot of the things that have been said in the last 2 days, I would completely undersign. But I think also we need theoretical foundations. Okay. And I want to list a few questions here. So for one, is there a good foundation for code and proof generation? At the moment, there isn't, but there's a lot of activity around this idea of model dependent type theory to scale sort of this logical foundation we have for meta programming in the simply type setting, for programming for regular programs, to the setting of proof languages. There's this idea of incomplete proofs, which is some work Alexander Nanevski and I and Frank Penning did, which led to this idea of contextual type theory. And most recently, it has really been used also as a foundation for program editors like Hazelnut. So you see kind of that synergy goes in both ways. Now, the second part I want to emphasize is that I think it's important to have challenge problems or case studies. And so Poplarmark back in 2005 was really kind of influential for the programming language community because it popularized this idea of using proof assistance. And it was a good problem that grad students could work on and play with and understand how to use proof assistance and how they could use it in their own work. Most recently, if you looked at Poplarmark Reloaded, together with people who worked on ACTA, COC, and systems like Beluga, and that really informs sort of best proof practices, across these kinds of proof assistance. And I think these kinds of challenges challenge problems become also important if you want to understand the power and role of emerging technologies like large language models. And the third point I want to make is really that we need more work on interactive and automatic proof development. Now, as I pointed out, there's a lot of boilerplate proofs that are currently required, and there's a lot of potential for proof reuse and automation. And I think Greg Morissette also pointed to this in his talk where he mentioned, really we need not only work on first order theorem proving, but we need work that allows us to do inductive proofs, smart lemma applications, and so on. And overall, I think we need a better understanding of automation. Sledgehammer as a tactic, which was mentioned earlier, is effective, but fundamentally what it does is essentially outsources a proof obligation and sends it to approvers like Z3 or Vampire. And what they do is then, if they succeed, they send back a list of clauses that are relevant. And then we kind of reconstruct this kind of proof with a verified resolution theorem prover within an actual proof assistant. So in some sense, these tools become, relevance filtering tools of what kind of lemmas and clauses are needed. So I want to conclude with sort of two lessons. Okay, so for one, I think we need really abstractions because they're key to the interplay of how humans interact with proof assistance and how we interact between interaction and automation. And in order to get these abstractions, we not only need new tools and engineering, but we also need new type theoretic foundations to provide these kinds of abstractions. And in fact, there are many domain-specific abstractions we can think of: heaps, linearity, resources, concurrency, and I'm sure in mathematics there are similar domain-specific abstractions we can think of. And the second point I want to make is that proof automation has really high potential for programming language proofs. So in some sense, it's a good test bed to experiment with proof automation, and that is because it's mostly clear what we actually want to prove, but the language itself is a moving target. And so in principle, we should be able to port the structure of proofs to new languages under investigation. Thank you.
Oh, wonderful. Thank you. So we will have the Q&A later. Just because we're a little bit ahead on time, I think, is it okay if I ask one question now? Or just curious about, just to elaborate on one thing. So I know you mentioned somewhere in here, you mentioned this like Poplarmark benchmark suite, which was super influential in kind of proofs about programming languages. So I know benchmarks are a really big thing in the machine learning community, become like really important if we want any task to be successful. So I'm curious, like what is it that you think made Poplarmark, successful? And do you think there are lessons kind of for other benchmark suites that we might build?
So I think it was very successful in bringing people to play with proof assistance. So I think there could be, in fact, maybe we already have enough mathematicians to play with Lean and proof assistance, but I think it's really a gateway for people to play with a new system. And so it wasn't a benchmark, as the TPTP library, which has like thousands and thousands of problems, and then we sort of run these theorem provers and see how many of these theorems can be proven. But it's a good benchmark to understand what kind of abstractions we want to support. So the original Poplarmark did highlight a lot this issue of variable binding in proofs and how do we model a context of assumptions in these kinds of proofs we deal with. And it did lead to library development and tool support. But I think its biggest impact was actually to make give a problem that was easily done within a day or two, and so grad students could easily learn a proof assistant, understand what the challenges were, understand what kind of techniques can be employed, and then sort of take this experience and use it in a larger setting. So I think that's kind of what I see maybe one of the biggest contributions of TotalMark in at that front.
I see, thank you. Okay, let's move to the next one. And thanks Brigitte, that was wonderful. So our next speaker will be Alex Nanevski. So Alex Nanevski is a research professor at IMDEA Software Institute, and his research is in the design and implementation of programming languages and logics, and in the construction of formal proofs in software verification, and in mathematics more generally. His recent focus has been on designing methods for integrating programming with pointers and concurrency into dependent type systems like those of the proof assistant Coq, with the goal of obtaining effective and scalable ways for reasoning about security and correctness of imperative programs. So with that, I will hand it over to Alex.
Thanks, Talia. Let me just figure out how to share my slides. Is it working?
It looks good, yeah.
Okay, so yeah, I will expand on some of Brigitte's points and the concepts that she introduced, but I'll try to specify them a little bit to the programming model of shared memory concurrency. So the title of my talk is Structuring the Proofs of Concurrent Programs. The idea being of structuring is, how to make them scale. And in particular, I want to connect this structuring idea to structured programming, which is a foundational idea in computer science, which was important at the time, 50s and 60s, because it was the first to suggest that how we write our programs matter. In particular, it was observed that if we allied the go-to command from our programs, well, that improves clarity, quality, and the development time. Now, that is relevant for this workshop, I think, because in particular, mechanized proving is a form of programming, as Brigitte has mentioned, and actually quite a few people in the previous talks. But just to reiterate, mechanized proving involves human instructing a computer on how to do certain proof steps and maybe how to generate its own proof steps at a certain point in time. But the instructions are stored as proof scripts, and that essentially looks like programming. So if there is a discipline of structured programming and mechanized proving is programming, well, can we say that do we need a discipline of structured mechanized proving or structured verification, let's say? And when is a proof structured? The answer I want to advance in this talk would be that the answer is yes, at least when it comes to verification of programs. I don't know about mathematics, but programs certainly. But the answer is not so simple as in the case of programming, because it doesn't involve just removing a certain program command like goto, but it's more application specific. Nevertheless, there is a common thread between different applications, and that common thread is this very idea that programming and proving are basically the same thing. That's not a coincidence. There is a formal result in computer science that goes by the name of Curry-Howard isomorphism that says that proofs in intuitionistic propositional logic are basically programs in lambda calculus. And the idea scales to quantifiers where instead of simply type lambda calculus, you suddenly have to talk about dependently type lambda calculus. So just to give you a gist of how it goes, let's say we have a judgment which says that the proposition A is true in propositional logic. Well, we can decorate that judgment with a proof, and that proof will be drawn from lambda calculus. In particular, we may have a rule like this, which says, reading it from the bottom up, that in order to prove that implication is true, you assume the antecedent and you prove the consequent. Well, if you decorate it with proofs, you get something like this, which says, in order to type check a function, you assume its argument and then you type check the body. And this scales to the quantified case as well. This idea of Curry-Howard isomorphism is foundational for the discipline of type theory, which is basically a study of program structures and types as their specifications. It is a limit point of the structured programming, and it is a foundation for basically all proof assistants, such as Nuprolukok, Lean, or Agda. However, it is fundamentally tied to the lambda calculus, and lambda calculus is a very specific programming language. It sometimes goes under the name of purely functional programming language, or we can say state-free programming language. It doesn't have state. Now that suffices to write proofs in math. It also suffices if you want to write proofs about programming languages, such as the ideas that Brigitte has mentioned. And it also even suffices if you want to write your programs in a purely functional lambda calculus, let's say such as a C compiler, and then verify it. But what do you do if you're actually interested in verifying programs which fall outside of the state-free paradigm? So what I want to go about in this talk is that type theory actually applies a bit more broadly. And we can remove this restriction on the purely functional lambda calculus while preserving the benefits to proof structuring that type theory gives us. And I will also explain what these benefits are. But as I said, I will focus on how we use the idea of types, independent types in particular, to write and specify programs in shared memory concurrent programming model. So when we started first with this, to develop a type theory for shared memory concurrency, we were looking for program logics on which to build. Whenever you want to do a type theory for something, it's good to start with a program logic for that something and then try to make it look like types. So we started from the earliest proposal, which goes back to Susan Nowicki and David Grease in 1976. So it's a very old paper. In fact, I mean, it's a classic paper, I should say. In that paper, they were looking at they were trying to design a Hoare logic. That means that they are building a program logic whose propositions, whose specifications come in the form that you see on the screen, which are called Hoare triples, where you judge that the program E has a precondition P and a postcondition Q. That is, if you run E in some state satisfying P and it terminates, then it gives you a state satisfying Q. And this is the example from the paper, they set out to prove that if you increment a shared variable X twice in parallel, then you move from the precondition which says that X is 0 to a precondition which says, well, you've incremented X twice. And here the syntax with angled brackets means that the stuff inside the angled brackets is executed without interference. That is, we first lock the whole world, execute, and then unlock. So basically only one thread can modify the shared variable X at a time. Interestingly, Nowicki Grease made a further requirement of the logic because they wanted to verify this program compositionally. What that means, well, without enumerating all the thread interleavings. In this particular case, enumerating all thread interleavings is actually easy because there's only two of them. Either the left thread goes first or the right thread goes first. But in general, if you have larger programs with more locking and unlocking, you can see that you get exponential explosion here. So it's essential to verify each thread separately and then have a way of putting these things together. Now, I won't go in detail through their solution and how they achieved it, but I'll just say there are two key ideas that they applied. And the first one is, well, you need to change your program. You need to annotate it with additional state and code that manipulates it, in this particular case, variables, global variables A and B, that capture how much the left thread, respectively the right thread, have added to X. That's their first idea. These variables go by the name of go state. Then the second idea is they introduce something that's called resource invariant. It is a proposition over the shared state which says how the state looks like when no thread holds the lock. And with that, it's easy for them to verify, let's say. I mean, they verify that the left thread and the right thread that the left thread increments A by 1, the right thread increments B by 1, and then by the resource invariant, they know that X is A plus B in the end, so it must be 2. Now, I want to draw your attention to this fact that this move that Nowicki and Grease have proposed, the first one, the go state, is actually a very type theoretic move because we are introducing new state and new codes, so new programs for the sole purpose of designing a proof. So already in that proposal, in their proposal in 1976, they have blurred the distinction a little bit between programs and proofs. And you see that, well, that matters in this case. Now, despite their work being very influential, it came up with a bunch of problems. In particular, let's say we want to prove that a three-way increment adds 3 to X. Well, the move is obvious. You add the third thread and you introduce a new global variable C, and then you need a new resource invariant which says that that X is equal A plus B plus C. But this is the problem because the two-thread subproof that maybe you have already done yesterday can be reused because it used a different resource invariant. In programming terms, we would say that the program state, in this particular case, the variable C, is leaked into the resource invariant. And that leads to all kinds of problems. In particular, we can't take an n-way increment and make it a procedure, because if tomorrow we want to use it in an n+1 increment, we actually have to reveal the code. And that leads to a lot of spurious proof obligation. You find yourself constantly proving the same thing over and over again, and you cannot actually abstract it as a lemma. To again use a programming concept, what you see here is a failure of information hiding and code reuse, except here instead of code reuse, we see a failure in proof reuse. So again, even in failure, we see the similarities between programming and proving arise. The situation is even worse because if you don't know how many threads your program is going to fork at statically, if you don't know how many at runtime, you don't know how many threads you're going to have, how are you going to annotate your program? So here on the screen, you see a program that iterates over an integer and forks, or for given input n, forks n threads, but it's not clear how many ghost variables to introduce because you don't know n upfront. In programming terms, we could say here that we have a failure of data abstraction because we cannot abstract our programming and figure out the number of number of ghost variables that we need. So how to disassociate the proofs from the number and topology of threads? Well, we'll bring types to help. In particular, we'll take the judgment from the OV-degree specification, the core triple now extended with a resource invariant, and we'll turn it into a type, a dependent type in this case, because both P and Q, as well as V actually, can depend on variables from outside context. And then we ask, well, what is a type for increment? Well, we have two increment programs in our example, one that's incrementing A and the other that's incrementing B. So we actually have two different types for increment and two different programs for increment. Well, we want to make this be the same because incrementation is incrementation. You shouldn't care whether you're incrementing A or B. Well, type theory teaches us that programs which differ only in the names of bound variables are actually the same program. So we lambda abstract the bound variable A in the first program and the lambda and the free variable B, I'm sorry, in the second program. So now we have made the two programs equal. But their types are still not equal because we have B variable free in the type of the first program and A variable free in the type of the second program. So we need one more abstraction. Now, this pattern of abstracting two variables is actually so pervasive in the examples that we decided to make a new type theory by promoting it as a default for the Horde triple type. In particular, what we have done is we have made every Horde type and every thread and every program to which we assign this Horde type have two local variables, which we call S, which stands for the abbreviation of self. It stands how much we have added to X, and O, which says how much other threads have added to X. And if we relate to the ghosts in the OV-degree example, in a three-way increment, the S of the left thread would be A, and its O would be B plus C. For the middle thread, it would be B and C plus A, and for the right thread, it would be C and A plus B. So the idea here is this S and O are local variables, so it means every thread has them, and they have the same name in every thread, but they have different values in different threads. Nevertheless, what should be apparent from this picture is that the sum of these two variables is the same in all threads. So we have disassociated the resource invariant from the number and the topology of threads. There is a little bit more to this story because these S and O variables cannot be independent. In particular, we have to capture the relation that an O variable of a certain thread equals the sum of S's of all other threads. I don't have time to go into how that's done. What suffices to say that those are two easy steps. And if you do them, what comes out is a generalization of a well-known logic that goes by the name of separation logic, which we have ended up reformulating as a type theory, actually. But let me just jump to examples. Now we have, for the incrementation program, we write one program, one ghost code annotation, and one proof, which says that this S variable is incrementing from 0 to 1. And they are integrated into and encapsulated into an object. What does that mean? Well, it means that all these three concepts together travel together through larger programs. So we can now do parallel composition, the examples that you have seen. And now on the left and on the right side of the parallel composition, we actually have the same program, the same proof, the same code. So proof reuse has been restored. Data abstractions has also been restored because now we can write our incrementation program, and you see the proof on the slide. Let me not go through it for the sake of time. And also thread topology is hidden by the types. For example, a program that performs, that forks n threads, each incrementing by 1, has the same type as a program which increments by n in one fell swoop. So the clients, which only depend on the type, will never be able to make a distinction between these two different programs. Now, these were very simple. This is a very simple example, but let me just mention that this actually does scale up. The plus operation can be replaced by any partial commutative monoid. The idea here being the monoidal structure. Well, commutativity and associativity are basically arise because parallel composition is commutative and associative, but unit stands for the contribution of the idle thread, and partiality captures that some threads may make contributions which are not, you cannot reconcile them. So some useful PCMs, for example, are heaps and histories. Heaps help you capture the state of your program. Histories, its time behavior. Both are finite maps from, in the case of heaps, pointers. In the case of histories, timestamps, so natural numbers are, both of them are natural numbers. The operation that replaces plus is disjoint union, capturing that you cannot have, two threads their histories cannot share an operation executed in the same time. And then empty map is the contribution of the idle thread. And we have applied these abstractions to very sophisticated specs and structures, things like stacks, concurrent stacks, queues, locks, readers, writers, locks, and so on. And that brings me to the conclusion. And the first is, if you look at the proofs and try to scale them, especially proofs of program correctness, the way to scale them is by improving how they behave in terms of information hiding and reuse. And these are ideas, these are programming ideas. And the point is that by Curry-Howard isomorphism, you can actually apply them to proofs. And what comes out, and in order to do that, you really have to figure out what are the abstractions, what are the concepts that you use to annotate your programs with, such as these two different ghost variables that I used before, in order to improve information hiding and reuse. And this is the connection with structured programming, because that also was about figuring out the right abstractions to express your programs. That leads us to the question of how to find right abstractions. Well, unfortunately, I don't have an answer here. I don't think this is actually what the research is. So there is no easy and straightforward path through it. But maybe this is what I'm hoping that AI can help us with. But my personal ways of finding these right abstractions is first use types. As I said, because if you want to scale your types, you need to use programming ideas and apply to them. Well, then use a framework in which programming ideas can be applied to proofs. And then finally, also experiment with proofs quite a lot. And this is also why I actually like and work on mechanization. Usually people say that mechanization is intended to increase our confidence in the correctness of our proofs and so on. For me, that's not the case. Really, the reason for me to use mechanization is as a laboratory for experimenting with proofs. So basically to gain insight in the structure of the problem, to learn what the problem is about. And well, I hope that AI, whatever contributions it has to this domain, actually ends up supporting this experimentation. And as a last point, I would say, because this connection between programming and proving exists, whatever contribution AI does for proofs should apply for programs and vice versa. So that's my talk. Thank you.
Thank you so much. All right, so now we have one more talk of this session. Just a reminder for folks to post questions on Slido. I see a few of them already, but after this next talk, we're going to have a nice long Q&A session, so there will be plenty of time to ask questions. So please post things there. So our third talk is by Avi Shinnar. And Avi is a senior research scientist at IBM at the Thomas J. Watson Research Center. He has significant expertise in the technical areas of programming languages and software engineering. His recent research topics include tooling for AI practitioners and formula verification of results in probability theory. So with that, I'll turn it over to Avi.
Okay, so I'm going to be talking about the usability of current tools for interactive theorem proving and what we would like to make them more usable. So first, why am I focusing on interactive? So I just want to be clear here, right? What are the possibilities? So we could just write proofs all on our own and ask the computer to verify them. And then the computer isn't really helping us much, but it is giving us confidence that at least we are correct. The other extreme we could imagine is we ask the computer, our magic AI system, prove Fermat's theorem, and we hit the go button, and eventually it comes back to us, hopefully telling us, yay, I proved your theorem. But of course, that's not realistic with the current state of the art. So what do we have? We have an interactive system where we work with the AI or we work with the computer system. So we type in our proofs and the computer tries to help us. And this is where hopefully AI can help with that interaction. Now, the current way this is done is generally an interactive theorem prover. So this is an example in Coq where you have a whole bunch of assumptions and you have something you're proving. This is a probabilities to theory statement. And you can see at the bottom, this destruct conditions as some gobbledygook is where we are going to do our first part of the proof. We're going to do case analysis. And the interactive theorem prover responds with saying, okay, there are 3 cases you have to prove. Here is the, for the first goal that you're going to start with, here are the assumptions, and then here is what you have to prove. Now, we can imagine here a number of places where machine learning tools could help with our experience. Let's broadly separate them into foreground and background kind of activities. So foreground activities are things like autocomplete, right? We're typing a tactic in like that destruct tactic, and maybe it can suggest what that gobbledygook should have been. Or I type apply and I want to apply a lemma now. And it would be lovely if the machine learning tool went and gave me some suggestions as to which lemma would be most helpful. We can also talk about some background tactics. So a frequent pattern when proving theorems is you start proving a theorem and then there's some fact that you need. Maybe it's a kind of structural fact, or maybe it's the really important thing, but I don't want to prove it right now. I want to just assume it's true and then see if it suffices to prove the rest of the theorem. So I put in an admit or a sorry statement and I keep going. It would be lovely in the background if the machine learning assistant could go ahead and get to work and either solve the problem or at least maybe come up with better suggestions for me for when I get back to it. One other thing I want to call out here is better names. One thing AIs have actually shown they're fairly good at is generating decent names for things, and that could be very helpful. So I know certainly in my development, in the code I was showing you, I'm sure there's something called Dvoretsky _helper_aux prime, maybe a 3. It would be great to have a better name, and that's a low bar in many cases because a lot of these lemmas, it's hard to come up with good names for them. As was mentioned earlier by Brigitta and Alex, and it was mentioned in the first day, and over the course of this workshop is that theorem proving is a form of software engineering. And so what do we want? We want IDEs, and they are as a way to both do interactive theorem proving and as a vehicle for machine learning tools to help us. So this is not obvious in the sense of the way current tools are set up is not necessarily designed for this. So let's take an example. This is off a website for one of these tools. This is a part of their demo. And how do you use it? Well, whenever you want help, you type in the suggest tactic and then you wait and the machine learning tool comes back and gives you ideas. That's very interruptive. Right, though people are used to something like Copilot or autocomplete, where as you're typing, if there's something to suggest, the AI machine through the IDE gives it to you. You shouldn't have to keep asking. Additionally, there's a problem that when you do ask, you end up generally having to wait for a while, and then you may or may not get results. And this is also not reasonable. People do not want to wait around to find out that there's nothing helpful anyway. As the point was made, I believe Johan and Greg made it on Monday. At that point, we'd rather just write the code or the proof ourselves. So on the other hand, in addition to the kind of nice, smooth foreground experience, IDEs also give a great way to give background information that's discoverable and actionable. So here's an example from a Python editor IDE where there's some linter complaining about one of my names to a function argument, and it doesn't make me stop what I'm doing. Instead, it just collects these in a problem view, along with other issues. And eventually when I get around to it, I can see in the code, there's also a marker there and a quick fix that suggests how to fix this problem. This could be a great way. Let's say there's an admit that the machine learning tool has figured out a way to prove. Then it can tell the IDE, and the IDE can make that information available for when I get around to looking at the admit. Similarly for variable names and renaming and stuff. One other note here is something else that IDEs are able to do, which can provide for better integration with machine learning, is this idea of templates. So in this example, right, I said I'm going to have 3 cases come out. So the IDE can actually add in stubs for those 3 cases along with admits for them. And the power of this is not just that it saves me a little bit of typing, but then while I'm starting to work on one of those admits, there are 2 other admits that are essentially going to be unchanged by whatever I do in that first case or whatever case I'm working on. And so in the background, the machine learning tool can kick off and start trying to either prove the admit or at least get ready to give better suggestions. I want to call out the Agda community, by the way, in particular, who developed this idea of holes and integrated the language with the IDE nicely for it. But as seen here, this can be done for any language. So how do we support this kind of IDE experience? So I mean, part of it, of course, is just software engineering. We need to actually build it. Instead of just having a tool that has a suggest mechanism, we need to have it say, write a LSP server. This is, again, this kind of thing is easier nowadays with new IDEs, like VS Code has a language server protocol, and it makes it much easier to funnel in these kind of autocomplete suggestions, for example. But there's also real research that needs to be done because the current machine learning tools for these systems don't really support these use cases. Instead, they focus on scaling up, and I claim we need to focus more on scaling down. What do I mean by that? So let's look at this example here. This is a recent paper on Balder, actually published by the moderator of the session, Talia. And what's the key experimental result from its abstract? That it can prove 65.7% of the theorems that in its benchmark suite fully automatically. And it's a great result. I'm not knocking this paper. And in fact, this is emblematic of the way papers in general are measured. But the problem is that's not really helpful to me as a user because I want, for example, in a foreground task, I want to know what can it give me now, not in 2 months of training, or eventually what can it might be able to prove automatically. So we need to focus not on proving more theorems like the current tools, but on getting results quicker, or in many cases. In general, there's a performance kind of trade-off, right? There's what the machine learning community calls performance, which is given a corpus, how many of the data, how many examples can you get the right answer for? So how many theorems can you solve? Then there's systems performance, which is how fast can we solve a given goal? And what we really need are systems that live on this trade-off and consciously and give you different points along it. So ideally it would be some kind of maybe online learning model or something like that, where as you spent more time, you were able to prove more and more complex things. But we don't actually need a single model, right? We actually could have a number of systems, say one system that works okay and scales up a little bit, but at some point, no matter how much more time you spend on it, it's not going to do better. And other systems that need more initial time, but scale to larger examples. And an IDE could navigate between these and choose which ones to call. Okay, I do want to quickly note there is a difference between training and inference and performance for them. So inference, which is given a theorem or given a point, and I say, I want help right now, giving help, that really needs to scale both up and down for foreground and background kind of tasks. Training can mostly be in the background with infrastructure support, but the difference does start getting fuzzy because as I'm writing an interactive proof, my current state and lemmas I've proven recently really matter and are very likely to be used heavily in the rest of the proof. And so they need to be taken into account. Okay, so reiterating this point that interactive theorem proving is a form of software engineering, and this point has been made over and over again over these 3 days. How do we build systems, right? We build them in composable or modular ways. So for example, we have Coq, that's both the language and the standard library, and then we might have some libraries. These are 2. Coq gives you a notion of extended reals with plus minus infinity and other things. And FLOQ gives you a model of IEEE floating point in case you would like pain as opposed to the nice happy reals. So these are libraries that are put out and maintained by other people. And then we have, say, the 4mm repository, which is the code that we're working on in our library. It probably lives in Git. And of course, then developers have it checked out on their machines. It looks like in the top right, they've actually proven their theorem. And then, of course, once some people have some success, they're going to put their code back in the main repository that everyone's sharing. So this is how we, as software engineers, we build systems. And this is not just for general programming systems, but for proofs that we're doing here as well. So my claim is that we need to do this for models as well. Current models essentially work on the whole world, and we need to figure out how, and this is a challenge to the research community, we need to figure out how to build models that compose. So for example, in this case, we want some kind of model that's built and fine-tuned or whatever you want to call it for Coq, and that can be put out essentially once per version. Then for popular or commonly used libraries, you want to build models of the libraries that reuse the information from the Coq model, that don't have to rebuild everything from scratch. And then we need a way to merge all that information together and then build upon it to have a model for our formal ML repository. And that should be much more lightweight, right? That we want to do maybe as part of our continuous integration system that can run overnight. But it needs to use, it really needs to use the information from these previous fine-tuned or however you want to call it models. And then locally, of course, these developers or these mathematicians or whoever the users are need to be able to have updated models that take into account their local changes. And it would actually be awesome if eventually when they put their changes back, instead of the formal ML having a system having to rebuild from scratch or using the libraries, if it could actually use some of the work done on those laptops and to build an updated formal ML model. Now, there's a few problems here. One is that we just simply don't know how to do this right now, or don't know how to do it well in approaching state-of-the-art performance. There is some research with fine-tuning and multi-prompt stuff. But the other issue is, right, a system like this is probably not actually going to get state-of-the-art performance that you could get by doing whole program analysis. And this is a thing that we're aware of, right? So like in the compiler community, if you write a whole program optimization on a compiler that works on the whole program, it's generally going to get better performance than something that's a separate compilation. But that ship sailed long ago. In general, we've agreed as a community that separate compilation is the way to go, because the only thing that scales to large programs and that works for everyone, that doesn't have some supercomputer with lots and lots and lots of memory. And yes, you lose some performance, but that's deemed an acceptable trade-off. And as a result of that becoming the norm, there's even then research of things like link time optimization to help ameliorate those costs. So as a community working on tooling for these kind of systems, I claim we need to invest in these kind of composable models, even if they don't get as performant as the whole model. Because right, so taking that Balder example before, I'm sorry to pick on you, Talia, that was a great system, but it took a long time to train on a large set of computers, and that's not really feasible for, say, me working with a formal ML project to do every night. I don't have the resources, it's a problem for the environment, and it's just a general issue that there is an inability of people that aren't at these large institutions to use these systems. And so we need composable systems, even if they lose some performance. And this is not just a research challenge, but a kind of institutional incentive problem that we need to motivate the publication of papers, even if the performance results are not as good as someone could get by doing something that is on the whole program. Right, so reiterating and recapping here, theorem proving is a form of software engineering. So like we want IDEs, and we really want IDE integration, and as a vehicle, both just for making our lives better, but particularly for enabling machine learning models to help us in a transparent, effective way. And we need models that can be fine-tuned for our specific domain, because one thing to note here is that when you're in math especially, every different kind of math, what you're really doing is you're building, for a given domain, you're building a new language, right, of definitions and lemmas and stuff. You're really building up a whole little language, and we need the AI system to understand that language. So we need to not just use one model for, say, Coq, but or general programming, but we need things that understand our domains. And in order to do that in a way that is usable, scalable, and works for everybody, we really need investment in composable models.
Awesome, thank you. So we will move to the Q&A in a second. I do I have a question for Avi first, just to follow up immediately on the talk, and then remember folks to ask questions in Slido. We have a long Q&A. I see some great questions already. So yeah, I think one thing, Avi, I'm curious about. So you talked about some kind of usability patterns that you saw in formal proofs, and I think sometimes, when I talk about these usability patterns, people have never used these before. And a lot of machine learning people, when they take on a task, are attacking a domain they've never used before, might be kind of surprised by them. So I'm curious if there are any kind of usability patterns you've either seen or experienced that you think might surprise either math people or AI people, and that could have interesting implications.
So I'm not sure. Let me first answer one question, and then you can check if that relates to it. I'm not sure exactly what you're asking, but okay. One thing I want to note, and this was a point actually made, I think, yesterday in one of the workshops, is there's a real disconnect between machine learning people and mathematicians and what they want, right? Because machine learning, their metric for is the system good is what percentage of theorems did I solve? So I have some corpus of, say, 1,000 theorems, and your goal is to get a higher and higher percent, right? But as a user, which is really in this case what mathematicians are, we couldn't care less. What we care about is we have this theorem right now. How can you help me? And that's a fundamentally different mindset. And that's what I was getting at this issue of not only do I want the result in a timely fashion, because a result that may or may not come, and that's the other issue, is the reliability. So a result that may or may not come in 2 months is totally, I wouldn't say totally not helpful. I mean, maybe I can leave it running in the background while I go do other things, but that's not on a general day-to-day basis helpful. I'm not sure if that quite addressed what you were asking though.
Yeah, no, I think it makes sense. Yeah. I think one of the things I've experienced, just to kind of piggyback on that, is like I think sometimes I don't even know what it is that I want to prove before I start. And a lot of the proving process is discovering that. So
two other points I should make there actually, because so one is, I think so putting on my doing formal math in the systems hat, as opposed to my machine learning hat, there's a lot of relatively low-hanging fruit, right? As a user, I actually am not so interested in, can it prove one more theorem in my library? I'm much more useful in, can it get rid of a lot of the stupid things that I shouldn't have to do? Because it would be lovely, and that's a great dream, and researchers should definitely work on making AIs able to handle more of the creative parts of math. But mostly I'm good with that, right? I can do that. Or if I can't, I'm not actually hopeful that machine learning right now in its current state is going to be able to either. But in the example that was given earlier, right, I believe Brigitte said that 70% of the theorems were these kind of stupid structural lemmas that have a very obvious form. They're the kind of thing which, if you have an intern, and unless they're really nice to them, right, you dump it on the intern, or you put it up for your undergrad. I mean, they're not fundamentally hard. They're annoying. And really, we shouldn't have to do them. And they're similar enough. One can imagine machine learning, learning from previous examples of how to do this and taking care of it. And that would be enormously helpful.
Yeah, that makes a lot of sense. Thanks for that. Yeah, so I'm going to open up to a few questions for everyone. I'll get to Slido questions soon. Just want to give more people a chance to ask things. In the meantime, this is kind of for everyone because we saw, all the way from the foundations of these tools into automation, usability. So I'm really curious, how you see all these things interacting. Do you think the foundations of these tools, the logical systems, type systems, notions of equality, are relevant to the kinds of automation that can or should be built? And similarly for, for what the user experience might look like, and how can we kind of make the most of all this interplay?
Yeah, so I want to address that actually, because I think that the work that Alex and Brigitte talked about are crucial. Because, and it relates to what I was saying about composability or abstraction, or there are all sorts of different terms for basically what PL people fall in love with. This is what, this is our byword. And the problem is that—
Can I interrupt you just for a second? This abstraction, that's precisely what you've been saying, like, can I get rid of proving these boring lemmas? I think if you get the right abstractions, your lemmas aren't going to be boring. And if they're boring, that's a failure of information hiding, and you should find better abstractions.
Right, you're totally agree with you, by the way. And actually that relates to an interesting question, to go back to Talia's original question for me, about that's one other thing that I would love AIs to do. I didn't call it out particularly in the slides for time, but is finding these kind of abstractions. Because I have to say, when I'm proving theorems all the time, I basically find that I'm like, it's pretty much the same proof as before, but I'm lazy, so I copy it. And the reason is because abstracting the right lemma is actually hard in many cases, because there is an underlying abstraction. But here, I'm just proving something as finite expectation. I don't care that much. I'm not building this deep theory of the domain where I care about what the right abstractions are. Maybe I should. I'm just saying in practice. And so it's just faster to copy the proof and tweak it a little than it is to really identify the right abstraction. And that's something I feel machine learning might actually be able to help with, is abstract out a lemma from the core parts of the proof. And that could actually give more insight into the proof as well. But I totally agree with you, Alex.
I would actually advise exactly the opposite. I mean, I also find myself very often in the cut and pasting mode, but then I really press myself not to do it and to actually pull out the abstraction, because I mean, when you figure out even what seems very simple can actually be an interesting result that it's a paper, you can publish it. Like this idea that I presented in my talk, which just these two variables, that is literally a way to invent separation logic had it not been invented already. And separation logic is basically the most, the most important idea in programming languages in the last 20 years or something, right? So, and it's, you can present a path to it just by sort of, as I did, right? Just by introducing a couple of more local variables, i.e. doing the abstraction.
So I totally agree, but I will point out that there's different modes of using this. And I think that happens for you most of the time because you're doing foundational work. And I do sort of a mix. When I'm doing more foundational stuff, I totally agree. But sometimes I'm functioning basically as a mathematician, literally collaborating with mathematicians. And we're proving things about Leibniz, not Leibniz, we're proving things about basically not Riemann integration mostly. We're mostly doing much more general integration and things about LP spaces, right? Martingales, fun stuff in probability theory. And this is often known math. I'm not trying to come up with a new abstraction, although sometimes some do fall out. I just want to get the proof done. And that's what I was saying. There are many cases where really the goal is the QED, is I want it done. And I would like machine learning to actually give me more insight than I'm willing to find on my own.
So this is all interesting because I think it kind of points to some kind of, there's also an interplay with like the domain that people are writing proofs for. Like we talk about writing proofs, but like all of math and all of programming is really large. So yeah, I think what that seems to point to is like an interaction also with the domains and what you might want, and even your personal style. Brigitte, I'm curious if you also have anything to add.
Yeah, I think I largely agree with Alex. And I think if you have the right abstractions, you can eliminate some of this boilerplate code. But what I also agree with Avi in some sense that you want automated tools that fail quickly and have quick feedback. And I think that is extremely important for usability. Where I actually see sort of AI methods could make a real difference is if you do these proofs, sometimes the proof search space might be still quite large, like even if you have the right abstraction. And just because you're proving something about a system that is inherently non-deterministic, for example. And so, then proof search will, it's just the system. It's inherently non-deterministic. Even if you think already about proving something about something like the natural reduction calculus, proof search over the natural reduction calculus is just not feasible. But often when we want to prove something, we have a certain clear idea of the structure of the proof. And so, even on paper, we might say, here, the case for conjunction goes like this, or the case for implication goes like this. And we would like to sort of transport the idea that we've described for one case over to others. And I think in that sense, I wish we could have smarter methods that could sort of abstract over what we've just done, not on the level of tactics really, but on the level of conceptual ideas, like what clauses we've used, what rules we've used, and identifying these kinds of patterns. I think that paired with like immediate, more timely feedback, because I think the notion of failure is actually really important. We need to fail quickly in order to make progress. For users to use it, we don't want to wait like a minute or 2 minutes. You don't want to wait 5 minutes. You don't want to wait an hour. And I think that's actually the success why type checking is so successful. Okay, so type checking is successful for programmers because it's instant feedback, and you can rerun it. It gives you precise error messages, and we've done a study where we use large language models and it gives you more precise error messages in principle. Okay, but I'm skeptical that we will use them in practice because the logical methods are just much more instantaneous in their feedback. And so it's, I think, a real challenge to incorporate these kinds of methods that maybe be more powerful, maybe give you more precise information, but they just take way too long in the feedback loop.
That makes sense. Yeah, so I'm gonna, sorry, do you have something to add, Avi?
Yeah, I just wanted to add, because I really liked your analysis of type systems. And one other key feature of type systems is that it's sort of understandable when there's an error, why, and programmers can build a good model for it. And part of the problem with the ZA tools is, in addition to, I'd actually be willing to wait a minute if I had some confidence it would work. But there's really no model for having any idea when a system is going to help me and when it isn't.
Yeah, that makes sense. You probably also want good feedback, like when it doesn't work, I would guess. So I want to just, while we're on the type checking side of things, there's a question in Slido. So this, there's a relationship between type checking, proof checking, depending on the foundations of the proof assistant. But someone asked kind of, backing up. So Garrett Mitchener asked, that there's sort of a meta question here, which is, how do you actually verify that the proof checker itself is correct? like who verifies the verifier?
Right. So, I think Thierry Coquon mentioned this already before, right? Like that we want to have a fairly small kernel. And the idea in the end is that this kernel has a very small theory, and that theory, ultimately the implementation of that theory is verified by humans. Okay. So you can certainly try and bootstrap, but I think understanding how to bootstrap, like how to build a theorem prover within a theorem prover, is really challenging still at the moment, because we don't have really the foundational theory for it. And that kind of, in the end, it basically means we need to rely on the human to verify the kernel. But I think it's important to have a verified small kernel, that we can actually understand. And so that's why I think actually it is important to think about, revisit what the kernel is. What is the kernel of a system like COP or ACTA or Lean? Because we do all kinds of other things. We do use templates and quote and unquote, we use metaprogramming, we use tactics, okay, and they're not part of the kernel, okay.
All right. Yeah, that makes sense. There's like a separation of concerns kind of between the automation and just the core proof checking part. It seems really nice for, what kinds of automation you can build. So yeah, speaking kind of more on the, type checking side, I will tie this into a question from Slido, but I actually want to start with kind of something even a little more general, which is like, do you think mathematicians really need these kind of like fancy logics and fancy type theories? Do you think there's something that they get out of this? And how would you convince a mathematician that it might be worth investing more in like the kind of foundations part of things, and that it might interact with what they can do?
Should I go? I mean, I don't know. The answer is I don't really know. But I liked, there was a talk 2 days ago where the speaker mentioned that lean people teamed up with a mathematician in order to mechanize that mathematician's theory. And the outcome was that the mathematician said, I forgot the names, I apologize, but the mathematician said that, yeah, now he has a better understanding of what has been going on. So yeah, I mean, for program verification, as I said in my talk, this, to me, mechanization matters because it is a way to understand the structure of the problem. I wonder whether that's the same for mathematicians. If it is, then, well, I guess they will take up on mechanizing. If it isn't, also be it.
Yeah, I think there are sort of these two sides, right? I think that once you start formalizing your theory in a proof assistant, you have to really rethink about a lot of the ideas that underlie your theory. And in some ways, it's sort of a joint endeavor, right? When you try to formalize something in a proof assistant, it sort of informs you how you think about the theory and what the structure of your proofs are. And ultimately, what you had on paper becomes somewhat simpler.
So the mechanization should lead to new math, basically.
That's right. Mechanization will, I think, by definition, lead to new math. I think there is another aspect, I think, which was often emphasized by Vladimir Bogovsky and other mathematicians, that there are, mathematical proofs also have bugs in them. And I think, there's some really interesting interviews with Vladimir Bogovsky where he's talking about like how I don't know, terrified he was that people would be reusing some theorems he had proven, but where he knew actually that there was a flaw in them. Okay, and so that was one of his motivations, really, was to use a proof assistant to bring in more certainty to the whole game of mathematics. I think both of these are valid, and I think the first point that also Alex was raising, right, that we will get new ways of developing proofs and theorems by sort of thinking in the ways of proof assistant is really an important aspect. It was also made by Bob Harper, I think, in the discussions on the Popplemark Challenge 20 years ago. So I think it's a common theme.
So to add to what they were saying, first of all, on the last point, math proofs, I mean, having mechanized a bunch of these things, they have mistakes all the time. The problem is convincing mathematicians the mistakes are a problem. And it sort of comes down to largely the software, and I would say most of the mistakes come down to the software engineering aspects of math, which is someone has a theorem which has some dependencies, essentially, some assumptions, a lot of which are technical. And sometimes they just get lazy, basically, about stating, oh, well, that function has to actually be measurable. Oh, that has to be LP1. I mean, there's all sorts of minor things which you tell them like, oh yeah, of course it does. We just assume everything is. But then sometimes they aren't assuming that. And at the end of the day, most of these wind up being resolvable, although there are some interesting cases where it's not. But that's part of the issue. Unfortunately, there's an issue in the math community trying to publish this kind of results that they're just like, hey, morally it was right, and the result is right, we don't care, roughly speaking. And I'm not saying they're wrong, I'm just saying there's a bit of a disconnect between our communities, I think, in terms of how much we care about those things. The other thing I want to do, and this also emphasizes, Brigitte, what you just talked about, and actually what Alex mentioned earlier about learning new abstractions. So an interesting case of this is, so I'm doing a bunch of probability theory kind of stuff and analysis right now in Coq. And there are many times where the textbooks will say, and turning the usual crank, and using the standard argument, blah, blah follows. No one, to the best of my knowledge, has ever abstracted out a lemma, which encapsulates the standard argument. For example, this comes up all the times when you're talking about things with integration, because integration is defined as something over a limit, over piecewise, simple functions, whatever. And essentially, you follow the standard mechanism of bringing your arguments through using various convergence theorems to get the final result you want. And everyone sort of has a feel for what the standard argument is. But that's a case where people don't really write it down as a lemma. So you're either left reproving the same kind of thing over and over, or figuring out, what Alex was saying and Brigitte was saying, figuring out what the actual lemma should be. And that might actually also be a bit of a case where sometimes the language is slightly changing underlying. I think this really gets to what you're saying about shifting foundations, right? The basic idea of the theorem we want to prove is actually sometimes similar, but over slightly different foundations. And so mathematicians actually do that. They just do it more intuitively.
I see. Thanks so much. Okay, so kind of then leading into something on Slido. Kind of a lot of the a lot of mathematics now happens in Lean. And so like Lean 4, for example, is kind of the newer version. Just in case people haven't used Lean, just, it's on a similar kind of foundations as the cockproof assistant, except that it has this like proof of relevance, like a different way of dealing with equality. I don't know. So someone is asking, like, in what ways, when do type theoretic foundations improve on those, from Lean 4? Like, if you're thinking about what Lean has, like, and you're trying to kind of build new type theoretic foundations from there and advance the state of the art, like, should you make something more expressive? Should there be more shorter term proofs? This is from Siddhartha Gadgil.
Well, the way I try to do it is that I first take, let's say, I'm trying to build a type theory for a program model. So you find some logic that has been published about it, and then you try to phrase it so that it's the specifications in that logic service types. And oftentimes you will be able to actually do to implement the semantics of those specifications as some kind of object in Coq or Lean or whatever, right? The key word, operational word here would be try to do shallow embedding, I would say. It would not always succeed. Sometimes you will be forced to go outside of the existing theorem prover. For example, you may need to add, I don't know, linear context or stuff like that, which is not there. But oftentimes you will be able to, to do something useful. So the key emphasis would be try to do shallow embedding. So try to do your specification through types rather than, and then use the native language of the theorem prover to write your programs, rather than do the deep embedding, which is, introduce a data type for abstract syntax and then try to do it that way. I mean, both approaches, sometimes you don't have the first approach. Sometimes you have to do the deep embedding because that's the nature of your problem. Let's say you're building a compiler and so on. But when the first approach works, it should be preferred because it will really lead to insight.
Cool. Does anyone have anything to add there?
Yeah, I mean, if I understood the question correctly, it was sort of how should we go about developing richer type theories? Is that?
Yeah, or even like what should the priorities be there? Like what would you want to improve on? And
right.
Yeah.
I mean, I think it needs to be informed by the practice, right? And so. I think the notion of linearity is a good example, right? Like, so should we have a linear type theory that has built-in support for linearity, or should we sort of build some infrastructure that generates this boilerplate code automatically? Or should we deal with linearity in completely different ways by having some explicit linearity predicate? That we don't know, right? But there are some things where I would say, there is a real need for new type theories. For example, the idea that we have metaprogramming. Metaprogramming exists in Lean, okay, but it doesn't have a real clear foundation as part of the characters of construction that is being implemented, because it uses this notion of quote. And now the question is, how can we actually prove properties about these metaprograms we have written? Well, you can't at the moment, okay, because it's not part of the kernel. And so for me, this is an example, where one maybe should revisit what the kernel actually is, because that is something it's important for people who use it. It's an important question for programmers as well as for their improvers, and maybe there we do need the new foundations. The same thing with the issue of equality, or what kind of equality do we want? I think that is something that needs to come from practice, and it needs to balance sort of how much support you want from automation versus interaction.
I could add a little bit here. So yeah, building new type theories, it's not always about capturing what kind of programs you want to be writing. It's also, as Brigitte said, what kind of sort of support for building proofs you want. And when it comes to that, I have learned that the stronger your type theory, the better. It can really save your life, the strength of the type theory. So that's why let's say I go with, calculus of constructions with Coq. I haven't used Lean, but yeah, I go with Coq. And in particular, I have found it very useful. The power of its type system is such that you can actually use it to do proof automation integrated within the type system. So not via tactics, but by other methods. And yeah, that's that feature, which goes by the name of type classes in Coq or canonical structures. It's super useful. So adding expressiveness to type theories of that nature is also something essential.
Thanks, that makes sense. Avi, do you have anything to add there?
Yeah, I just want to note, and this relates, but actually particularly to something I believe Brigitte said about the desire to, for example, prove that your meta theory is, or sorry, your meta functions are correct. That we, I think, want to be careful of trying to dump too much in the kernel. And this relates to the question asked about how do we trust that these things actually work? So we really want our core type theory and kernel that we're checking to be actually as small as possible. But we want, the key thing is that it supports layering abstractions on top of it. So rather than have one that has a linear system, I'm not against that, but I would rather one that enabled me to build a linear system around it and prove that it was correct. And then people can use that abstraction, but they don't have to trust it. This is sort of maybe similar to the Isabelle Hall style, where you have a core logic under, and then you build on top of it Hall, and you build under logics on top, although I like the Coq type theory better. I'm not personally, for reasons similar to what Alex said. So I think that is more important than the details of how, right. So rather than try to make our core logic more expressive, we need to build expressive logics and ensure they can be supported on top of our core system.
But I think of it more like as a compilation, right? You have a richer type theory, and then you compile it into a core type theory. So, I mean, I think there's a lot to be learned, right, from compilation programming languages, right? Higher level languages, like, I don't know, ML and Haskell or Camel, they have all kinds of features, right? And then we compile them in lower level languages like C or even lower down, right? And so in some sense, I think I would wish that there's more compilation in that front, right, for proof of systems, because in some way, I would say we're still a bit like in the lower level side of things when you work with something like the characters of construction.
Thanks. Yeah, this is all super interesting. I feel like I've seen things on kind of both sides. Like in Lean, I know one of the most widely used things by mathematicians are like the classical axioms, even though the foundations are not classical. And the fact that it's just an axiom that it sticks on top doesn't seem to matter that much to most people, so much that I've heard mathematicians say that Lean is like a classical proof assistant. Then on the other hand, I've done like proofs about my proof automation and having a really rich notion of equality. Like I've been in cubicle type theory recently, just so I can relate proofs to each other, which has been really cool. So this is all interesting. So there was a little bit of talk there about kind of the levels on top of the kind of core like language of proofs, the logical proofs that are being checked. So things like tactics or metaprogramming and so on. So there's a question on Slido asking, so it says there seems to be a lot of progress in proof environments directed towards human use with like syntactic sugar, tactics, and so on as examples. But is there any research directed towards machine use? Like it might be that the two, like what's useful to humans and what's useful to machines might be different from each other. Yeah.
Well, I don't know. But Dijkstra famously said that we should be writing programs for humans and then have machines adapt to us rather than vice versa. Yeah, these are high-level programming languages. So I'd say everything is targeted to humans. I'm not sure about machines. That said, there is a distinction, let's say, if you are writing, let's say, a proof in Coq, for example, and you come up with a certain proof script. I would not say that that's, human. I would not say that's English. It's not the same as writing the same proof out, ready for as a homework, let's say in your math class or something like that. So maybe in that respect, writing such proof script is more like writing a program in a programming language, more machine-oriented than human-oriented. So I guess there's levels to all of this.
So, I would note that this is like my second slide of my talk, right? Why are we talking about interactive theorem proving? It's because we fundamentally want humans and computers to be able to work together on this, because otherwise we're either in the state that computers aren't helping, or if the computer can't do the whole problem, it's over. And we're the weak link, right? So we need these things to be designed for us. The computer can adapt pretty easily. You can literally just compile into some other format the computer understands better. That's what we do. So whether there is an interesting question of whether there are better like theoretical foundations that somehow make it easier. My guess, though, is from what we understand so far, no, in some sense, because really what helps is abstraction, right? Is the ability to build these layers of abstraction that simplify the problem and that simplify the search space. And that's as important for humans as it is for computers.
Yeah, anyone have anything to add there? Okay.
I don't know. I think, if you think about program synthesis, for example, I would imagine this is done better for higher level languages, that rather than lower level languages. And so in that sense, we as humans enjoy reading maybe programs written in a higher level language a little bit more, and proofs that live maybe on a higher level setting. And I think in the end, tools like program synthesis might be also more effective for such high level languages, because we can don't need to sort of talk about registers that get allocated and so on, right? So I think there's not exclusive. That's what I'm trying to say.
I like what Avi said also when he said that, figuring out these levels of finding the right abstractions is good both for machine and for the human. And that's absolutely true. And that goes back to this point of his, dilemmas being boring or not, right? Dilemmas are boring if your proofs are, if you're type checking issues, proof obligations that are spurious, that are repetitive, that are whatnot. But if you find the right abstractions, then you avoid generating this, and therefore you also don't have to think of a machine supported way to discharge them. They're just not there. That's it. So that improves, that's good for the human as well as for the machine, right?
Yeah, that makes sense. This is all interesting. I guess I have a question that's a little bit tangential, but this is all making me really curious about. So this one's coming from me and it's for everyone. Sometimes when people talk about proof assistance, they kind of talk about it as it's a barrier to use. I would be writing this by hand, then it'd be really easy. If I write it with the proof assistant, it's going to be harder, but then I'll get stronger guarantees. And I've heard this frame, but some of you kind of mentioned, like Alex mentioned, proof assistance as a playground. I think I've also had this experience. So I'm curious if any of you have had an experience of a proof assistant making it easier to prove something that you actually didn't know how to prove by hand. And if so, what was that like?
Oh, yes, I can answer that. Particularly when doing kind of programming language kind of stuff. I, many years ago, stopped doing the proofs by hand first and started just doing them in the interactive theorem improvement first, because the software engineering, just managing all the cases, it's just so, instead of having to think deeply about what cases are going to come, you just ask the computer, okay, I'm doing induction, what cases do I have to solve? And then you can very quickly winnow out the boring ones and either have automation or a lemma or however to handle, sometimes the base case is easy, sometimes some of these are easy. You figure out the hard one, and then there's this interaction that happens a lot. And I claim it's not just an interactive theorem proving, it's on paper too, it's just messier on paper, is as you're doing the proof, you discover your definitions were wrong and you tweak your definition and then you go back. And on paper, the problem is it's unclear what part of your proofs you have to throw away and what parts you reuse. So when I used to do this, right, you'd write out like half a page of proof with some random Greek letters, and then you'd go, oh shoot, I missed something. And then you'd sort of have this feeling, well, that only has a local change, so I can leave those parts of the proof alone, and hopefully I got it right. And then maybe if I'm really feeling good about my thing, then I'll, if I'm really feeling like a good, doing my due diligence, at the very end, I'll go back and re-verify everything, maybe, right? It's hard though, it's a pain. Whereas in the theorem prover, it just gives it to you. You go tweak the definition, most of your proof still goes through. The parts that don't, you fix. It sort of takes care of all those details, and it gives me confidence I got them right. Particularly when doing, by the way, some tricky inductions where I literally had more faith in getting it from the computer than making sure that this double induction worked. And in all cases, my thing went down, and it's just easier to get right.
Yeah, I do the same. Basically, these days, I don't even like try anything on paper. You immediately go. I mean, when you're doing program verification, especially in the case of concurrency, I mean, and especially when you have an experimental system that's not even published yet, and maybe it's not even ready to be published because whichever solution you've currently implemented is just a bad idea, right? You cannot do it on paper because you may be overwhelmed by proof obligations. But then the point is, you see why they are arising, what's the problem, and then you try to organize your system, your logic, so that those don't arise. You push the bubble, you come up with new definitions and so on, and yeah, that's how you fix the issue. But it's essential that you play in a tool right away rather than doing it on paper, because I mean, I just don't even know how to think on paper anymore, quite frankly.
Yeah, can I add one more comment there, which is something just to be clear for people that are getting into it is doing it in interactive theorem prover does not mean you have to prove everything. So in that study where 70% of the theorems were structural, you don't, when you're exploring and trying to understand language, actually have to prove all those. You can just state them. This comes back to what I said. All the time, there's this pattern where you just admit things. So you can state, oh yeah, those substitutions commute with each other, admitted, done. Now, obviously, if you want to have a full final system, you need to go back and prove it. But if you have reasonable confidence, it's not like because you're working with a computer, now you're stuck proving all these details as part of your exploratory phase. You can explore just fine.
Yeah, there is also, I guess, the point that there is a way to use these tools in a wrong way, because they are very expressive tools, and they have, sometimes one and the same thing you can say in a couple of different ways. And if you choose the wrong way, then, it's proof hell. And if you choose the right way, then it's beautiful, right? And in the early days, I remember the books were even teaching people to use, let's say, the distinction between index and parametric types families in Coq. And the books were telling you use index when you really wanted to use parametric, and then your proofs would just explode. And I remember that put off quite a few of my friends from, they fired Coq once, tried to do to prove that adding, concatenating two lists adds their sizes, and then failed miserably for such a simple thing, and then gave up. But in fact, if you just use the other thing, the other abstraction to say what you need to say in this particular example, the proof is like a half a liner, right? So there is such a thing too. So one has to be cognizant of that. There is a wrong way to use these tools.
Cool. Brigitte, did you have anything to add?
I guess I'm still doing a lot of proofs on paper, I must admit, although I'm building my own theorem provers. But yes, I definitely, all my grad students, would completely agree with what Alex and Abby have been saying. And I think it is also true that you discover sort of subtleties in the proof and you actually try to push them through in a theorem prover. So I completely agree with everything they said.
That makes sense. Yeah. It's all interesting. I tend to go back and forth just to inject my own kind of usability pattern there. It's like I'll usually start in a proof assistant, try to figure out what I want to prove, go back onto paper, figure out what's missing, go back to the proof assistant. It's kind of a fun workflow, have extra tools. So let's see, there is a question that's, this is from Mark Herman on Slido. And I think it's important just because we have a lot of, people like mathematicians who are watching all of this. So Mark Herman asks, are there any introductory books or papers you would recommend to math grad students who want to learn more about, this topic, especially for someone who has never heard of proof assistance before this workshop?
I guess I could recommend Ilya Sergey's, I don't know, I forgot the name of his book. It was lecture notes from a summer school he gave. That's one of the more recent, I guess, entries into the documentation.
I mean, I think it's really, would be really great if some people came up with something similar to Popplemark, because I think that for mathematicians, I don't know what the right Popplemark equivalent would be for mathematicians, but I think it really provided an entry point for many, many people in PL, because it was a small enough challenge problem. Okay, people could read it within like a couple of hours. They could even do it within 1 or 2 days, depending on how much they already knew. They could do it in simple ways and fancy ways. So they could really kind of explore this kind of design space. Also, what Avi and Alex were talking about, really kind of this kind of exploration of the system. And that would be my advice. Okay, that we really need in some way sort of these small enough problems that highlight how you go about solving it and where you sort of find the fun in it as well, right? Like some people were saying, it's a bit like a game, right? And so and people also enjoy it in some way, right?
So I guess I can add, I don't have any great references offhand, but I will comment similar to what you were suggesting about Popplemark is, right now there's this sort of issue, right? So we have some of these great libraries. So for example, if you're a mathematician that wants to get into it, you might pick up Lean because there's this MathLib library that's been working really hard on formalizing a whole bunch of math. But especially if you're, say, early, you're not like an advanced, you really understand the deeper math, they can be hard to get into because they often, again, some of this may have been addressed a bit in Lean, so apologies, I'm not an expert at MathLib. But you want to do, say, integration, and you suddenly discover, oh, we're working over an arbitrary Hilbert space or something like that. And you use these concepts, which are perfectly great, and they're a great way to build it. But if you're a second-year undergrad, you have no idea what a Hilbert, you might have no idea what a Hilbert space is. You just wanted to try out proving this theorem from basic year analysis class. And bridging that gap can be hard. And that's true even, like, for example, Cocklicot, right, which we were using, is great and has this wonderful system, but it builds it all out of the language of filters. Most math papers don't. They do it based on limits. And so just bridging that notation, that gap in terms of meaning can actually be quite a challenge, even for a working mathematician. So I think there is a need for like learning ramps, like say MathLib. So a learning ramp where you have a version of it which uses simpler concepts and isn't as powerful, but allows for an easy playground for people to explore.
Thanks, that makes sense. So from some of the other moderators, they're just like people getting excited and posting more resources. So I think one of them that comes up is this book. This is from Heather and Ursula together, Mathematics in Lean, and also the related like Xena project, which has, I think, like most of the stuff should be in that book apparently, but it's a good starting point to find interesting things. Yeah, there's also a Lean game, and yeah, I don't know. There's also a cubicle game, which is really fun if you're into like topology and stuff. This is me, actually. This is me talking now. But yeah, I played a cubicle type theory game, which like that was super fun from like a topological perspective. So yeah, there's a lot. I think maybe one of the cool things we could do after this workshop is just put together like some resources, because we're all coming from these different areas. So I feel like that might be a really nice outcome. Yeah. Okay, I think we want to start wrapping up. We have the next session soon. Maybe I'll ask like one concluding question. Let's see. Yeah, I guess maybe just to go back to kind of a high level thing, like a lot of you mentioned kind of a lot of really interesting problems, like maybe too many to start on. So, if someone wants to go and work on something like really impactful right now, maybe like what's the one problem that you are most excited about?
Well, I like what I'm
that's the
working.
one we're working on ourselves.
Sure, yeah, maybe the one you're most excited about and don't have time to work on.
Well, okay, so I can tell something where it actually makes sense. So all of this is all the work that all three of us have been mentioning is compositional this, compositional that. And for me, I guess one big thing that I hope to find time in the future to work on and find collaborators to work on is compositional, let's say, type theory for cryptography. So I know that there have been, works in the crypto world on making compositional models for working with cryptography, and I think there ought to be a huge connection between those and type theory.
Yeah, I guess I'm a computer scientist, so what I think is a really interesting question. We have this lambda calculus. Also, Alex was talking about as a foundation for programming, and at the same time, we have process calculi that gave us a foundation for concurrent programming and concurrent computation. But if you think about type theory, there's really no type theory for concurrent process calculi. And so, rethinking like what this type theory would be looking like is, I think, would be a really interesting question. Because right now, when you want to have this foundation for concurrent systems, which is based on this process calculi, they're kind of simple types. Again, there's nothing like dependent types, and it's not even clear what this notion of dependent concurrent process computation or types should mean. And so I think that's, for me, one of an interesting question. Maybe not for mathematicians so much, but for computer scientists, I think it matters.
So I guess I'll go address a different audience, which is the machine learning audience that's working on these tools, and say what I think I would really love them working on is the low-hanging fruit. Because right now, the focus really is sort of internal, is how can we get better results that let us claim we've done better? But none of that is really helping people using these systems. They're not helping mathematicians formalize math. So I'd really love this kind of scaling down to low-hanging fruit so that it can actually help mathematicians. Like a lot of these annoying things, mathematicians don't want to do it because there's all these details that they just know are going to work out and they don't want to prove. And those are ripe fruit for machine learning to prove for them.
Awesome, thank you. All right, so let's move on to the next session. So our next session is going to be, thanks everyone, sorry. Thanks to all the speakers, fantastic. So our next moderator is Brendan Hassett, and will be leading a session on research advances in mathematical sciences. Thanks.
Thanks a lot. My name is Brendan Hassett. I'm a professor of mathematics at Brown University. And I'd like to introduce the colleagues that are presenting in this session. So the first colleague is literally a colleague because he works at Brown. Javier Gomez-Serrano is associate professor of mathematics at Brown. His research on the boundary of, his research is at the boundary between analysis, partial differential equations, fluid mechanics, spectral geometry, and numerical computation, with a specific focus on rigorous computer-assisted proofs. He's been especially successful in the interplay between rigorous computer calculations and traditional mathematics, leading to computer-assisted proofs of important results in partial differential equations. Adam Topaz is an assistant professor in the Department of Mathematical and Statistical Sciences at the University of Alberta. His research focus is in arithmetic and algebraic geometry, especially Abelian geometry and Galois theory. But he's also been formulating mathematics since 2020 and is one of the maintainers of Lean's formalized mathematics library. And finally, Alex Kontorovich is a professor in the Department of Mathematics at Rutgers University. His research focus is in number theory, geometry, and dynamics. He's received recognitions from the Sloan Foundation, the Simons Foundation Fellowship, and the von Neumann Fellowship at the Institute for Advanced Study. He also serves on the Scientific Advisory Board of Quantum Magazine and is Dean of Academic Content at the National Museum of Mathematics. So let me hand the baton to Javi. Javi, are you ready yet?
Yes.
Great.
Let me share. Just give me 1 second. I'll start sharing. Okay. Can you see it?
Perfect. Thank you.
Great. Yeah, thanks a lot, Brendan, and yeah, thanks a lot for the invitation. It's really an honor to talk at this workshop. So today I'm going to talk about yes.
Can you put into full screen mode?
I am in full screen mode.
That's not what we're seeing on our side.
Okay. Is it better like this? Maybe let me stop sharing and reshare.
That's probably a good idea.
Okay, sorry about that. Is it
Much better,
now?
thank you. Yep.
Okay, great. Yes, so I'm going to talk about recent advances in the interplay between artificial intelligence and mathematics, and involving also computer-assisted proofs. So before I start, let me give a very small disclaimer. This is going to be a highly speculative talk, so I'm going to talk about what we have been successful so far in doing, but I'm also going to talk especially where we're headed to and what we are trying to understand and where we are trying to get to go. Having said that, we're just starting and we have only scratched the surface of what it can be done. So I feel that even though AI and mathematics have a short history, let's say, of working together and interacting together, I definitely foresee a very long future and lots of avenues for collaboration and interplay between these two disciplines. And I'll be more specific to that later on. So just to give a feeling of where I come from and sort of how I got into this business, just a very 3-line summary of my background. So I did a lot of competitive coding as an undergrad. I went for a short time to industry. And I got a PhD in partial differential equations, so more like, let's say, traditional pen and paper stuff. I've been doing computer-assisted proofs for the last 10 years or so, and lately I've been interested in machine learning as well. So just to highlight what I want to say is that it's important to train mathematicians in machine learning, because I think in the future this is going to be like a very good tool, and it's going to be quite useful in many branches of math. So it's important to keep interdisciplinary profiles and train people both ways, so they can talk to each other. So I'm sort of starting from the end. This is where we are trying to get, and this is what I'm interested in. So I'm interested in the equations coming from fluid mechanics, and particularly in the 3D incompressible Euler and the 3D incompressible Navier-Stokes. So the Euler is the second PDE ever written. It's a 250-year-old, notoriously hard problem where we have Newton's law. U is an incompressible velocity, P is the pressure, and nu is a number accounting for friction, for viscosity. If nu is 0, then this is the implicit case. It's the Euler equations. If nu is positive, then it's the Navier-Stokes equation. And the open problem is to say whether if you start from nice, smooth, finite energy initial data, is there going to be a finite time singularity? Is there some quantity that will become infinite in finite time? And for Euler, this is a very old open problem. For Navier-Stokes, this is one of the Millennium Prize problems. So it's a very famous and really hard question that we're sort of aiming towards. Now, from the perspective of the numerical analysis and the numerical simulations community, the story is the following. So the way things sort of advanced was, well, first of all, there was, up until recently, there was no consensus whether the answer should be yes or no. So it's a lot harder to prove a theorem if you're not really sure whether the answer is one or the other. And then typically the way these things used to work is that somebody had, let's say, the fastest computers in the world, run a very, very long time-consuming simulation, got a scenario where things seem to be about to blow up, and then published a paper. So far, so good. That's great. But then this has issues. So one of the issues is that it's difficult to replicate. There's only one group who has the biggest supercomputer in the world and the capability to perform these like monstrously long calculations. So it's quite slow. But then the thing is, after a few years where, let's say, software and hardware had improved, then other group had the biggest supercomputer in the world, and they have the capability to run these things, rerun the old scenarios, and discover that, oh, wait, so what we actually had and we believed that led to finite time singularity, actually, if you compute with higher precision, if you compute better, longer, then it's not really a singularity. So this is also highlighting the need of like a rigorous proof and verification of the numerical scenario. So this is a small snapshot of how the community has evolved, and you can see different answers like yes, no, recalculation, no. And I'm going to highlight this red paper from 2014 by Guo Luo and Tom Hao. So I'm going to talk more about this scenario. So this is their scenario. It's about 10 years old. It's a breakthrough. And what they did was they considered a fluid setting inside the cylinder. The setup is axisymmetric, and the fluid spins one way on the top half and the other way on the bottom half, and this generates secondary currents that eventually lead to a finite time singularity in the z is equal to 0 plane, r is equal to 1. So on the boundary of the middle of the cylinder, and they did a very extensive, very thoughtful calculation, and they were observing a growth by a factor of 10 to the 8, which was beating the current world record by a massive amount. So this was extremely compelling, and moreover, the numerics suggested an asymptotically self-similar scaling at the time of blow-up. So what is self-similar blow-up or asymptotically self-similar blow-up? So it's something like this. Oops. Well, there. Okay, it's not really working, the animation. But as you zoom in, as you approach the singularity, then you sort of converge to a rescale profile that keeps being more or less the same. If you zoom at the correct rate as you approach the finite time singularity. So this is the object that we're actually going to look for, the self-similar profile. So we didn't have that many resources and we didn't have that much time. So what we came up was to use machine learning. And in this context, in this specifically of like self-similar singularities for fluid equations, we were the first ones to do this thing, and we were successful. So what we did was essentially try to find a solution of the PDE using artificial intelligence and concretely using something called physics-informed neural networks, which was developed by George Karnelakis and his group, also from Brown, and it's something that is immensely popular. So it's a 4-year-old paper. It has 5,500 citations. This is about 4 citations per day. So extremely popular, and it is much faster than traditional methods. So our simulations took a few hours. And I think that it's not so much about the speed, because the speed, you can always buy new hardware, you can buy new software, you can get more computational resources. But the thing is about discovery. So I think the important role that AI has played in our results is discovery, because like these solutions, nobody knows if they exist or not. And then you start simulating and you start thinking like, well, I'm failing. Why am I failing? Am I failing because of me? or am I failing because there's nothing there? And eventually you sort of give up because you don't find anything, and then you think, well, maybe there is nothing there. Now, what AI has managed to provide for us is this discovery of new solutions that are isolated, far from anything, and nobody knows how to compute them using, let's say, more traditional methods. The solutions are unstable and they haven't been observed before. So this is, I think, where the big value of AI for us has appeared. So these are the solutions that we found. These are solutions, similar solutions for something called the Boussinesq equation, which I'm not going to describe, but it's a closed Gaussian of 3D Euler, 3D axisymmetric Euler. And if you understand well the Boussinesq equation, then you can understand well the 3D Euler axisymmetric scenario. And we can see that the errors are quite small compared to the size of the functions. So after posting the paper and after posting the preprint, then we got some attention from Quanta. So Quanta highlighted the connection between deep learning, math, and sort of how this new approach to machine learning could lead to finite time singularities. Okay, so what I mean to say by doing this talk is not just, okay, we should drop everything that we're doing and we should all do machine learning and forget about the math and let the machines take over and do the thing for us. So what I'm suggesting is somehow the coexistence of these two things. So traditional methods are still very useful, they are widely available. But what I'm advocating for is, first of all, the combined use of these techniques. And second, the more prominent use of computer-assisted proofs, machine learning, and computers in general in the field of mathematics, and not just, let's say, as a small tool or just to provide insight, but having more and more importance as time goes by. So Chen and Hao released two preprints in 2022 and 2023 with a computer-assisted proof that doesn't use AI, but uses interval arithmetic of the Luo-Hao scenario, which is stable. Okay. Now, PIN, in our experience, is quite versatile. It can attack other equations, and we've been successful in finding other subsimilar equations for other equations, which were impossible until now, and nobody had discovered. So we have, for example, been successful in finding solutions for something called the CCF model, and other equations, and we are now writing up part of our results, and we'll post the paper soon. So the plan moving forward is to go towards Euler and Navier-Stokes and remove the boundary. So this is more or less how we feel that the proof may work. Step one, find an approximate subsimilar solution, either using machine learning or using some other method. We feel that AI has the edge here because it can find these isolated things, new things quickly. Then prove linear stability or perhaps tolerating some degree of instability around these solutions. Use interval arithmetic, use a computer-assisted proof, bound everything rigorously, and then upgrade the linear stability to nonlinear stability. And the upshot of this approach is that I never told you what the PDE was. So it's really agnostic to the PDE as long as your approximate similar solution is good enough. So we're not really using any structure or in a crucial way, we're not using a lot of the equation itself. And this is good because it's a universal strategy, and it is likely that it works in many cases. So these are the people that I've been working with for the last years. We share a connection to Princeton. We were all at Princeton at some point and overlapped for a few years. It is maybe uncommon, but not unheard of. Mathematicians who work together with geophysicists who were into the machine learning business before us. But perhaps it is more uncommon to also collaborate with industry and to use industrial resources to kind of ramp up the scale of the project. Because this is, or we feel that this is something that could apply to several problems, and it's not just related to one particular equation or one particular method. We feel that this way of looking at things needs to be better understood, but also has a lot of future going forward. And we do have graduate students working in this kind of problems. Let me make a 10 seconds advertisement for Yongji, who is going to be on the market next year, and people should hire him. So we've been recently funded by NSF through an FRG grant and our individual NSFs. And let me just finish this talk by summarizing it, saying that this is a very vibrant field with lots of recent progress. Many things have been happening in the last 5 years, and it's leading to new paradigms, new avenues of research involving computer-assisted proofs and machine learning and the interaction of both of them with mathematics. And we definitely see many big successes in the near future. So please stay tuned, and thank you so much for your attention.
Thank you very much, Javi. So I think we'll probably do questions after everyone has done their initial presentations. I just want to remind the audience that they can make their own questions or queries or comments through the Slido system. And so we'll definitely rely on that in the discussion at the end. I think Adam is the next person slated to speak. So Adam, are you ready to start?
Yeah, can you hear me?
I can hear you great.
Okay, let me share my slides here. Okay. Can you see the slides okay?
Yes.
Okay. Yeah, so let me start by thanking the organizers for inviting me to speak in this very exciting workshop. As Brendan mentioned, I'm primarily a pure mathematician. I work in arithmetic geometry, mostly in abelian geometry, but I'm also interested in formalizing mathematics. And what I'll talk about today is some of my experiences in formalizing research level mathematics and somehow some hopes for the future of interaction with AI. So first, let me start with maybe the slogan for my talk, which has been reiterated multiple times throughout the week, or I guess throughout the last 3 days. And this is the way I see how formal methods can interact with artificial intelligence. I see it as somehow as a bridge between neural machine learning methods, AI methods, and the more strict regime of mathematics. Before I start, let me make a distinction in formal mathematics in general between library building and research mathematics. So building formal libraries has been discussed multiple times in Johan's talk and Jeremy's talk in particular. And building libraries, essentially the goal is to capture some segment of mathematical knowledge in a formal system. For example, one of the main stated goals of Lean's MathLib, the main mathematical library of the Lean theorem prover, is to capture a whole undergraduate curriculum, and we're quite close to this point. And of course, eventually, the goal is to go beyond the undergraduate curriculum, but that was one of the stated goals. Usually, these libraries are meant to be used in other formalization endeavors, such as projects formalizing more advanced mathematics, which I'll talk about later. And they have large and many contributors. They're large and they have many contributors. So I mentioned, what's going on here? I mentioned MathLib. Let me just say a few words about this in particular. MathLib is Lean's formalized math library. It has over 300 contributors, 23 maintainers, over 1 million lines of code. This is Lean 3. The Lean 3 version has over 1 million lines of code. The Lean 4 version will probably have more. And of course, it's still growing. And we have formalized results from algebra, topology, category theory, and so on. So a very broad spectrum of formalized mathematics. On the other hand, and this is what I'll focus on mostly for the rest of the talk, there's the issue of formalizing research level mathematics. These projects are usually more focused. They use the libraries, the formalized mathematics libraries. They usually have fewer contributors and more direct collaboration. So let me just touch upon this last point a little bit more. In MathLib in particular, at least it seems to me that work is usually done more or less separately. Maybe a small group of people or one person would work on a particular subject, open a pull request, and so on. And in contrast, projects like the liquid tensor experiment, which I'll talk about in a moment, have more direct collaboration. That I'm not saying that there are few collaborators. As I'll mention in a second, the liquid tensor experiment had a good number of collaborators, especially in comparison with the size of collaborations in pure mathematics. But I would say that the collaboration is more direct in such projects. Okay, so the example that I'll mention here is the liquid tensor experiment. It's been mentioned a few times already in the last couple of days. This stemmed from a challenge posed by Peter Schulze to the formalized mathematics community to formally verify one of his main new theorems in the context of condensed mathematics. The project itself involved about a dozen contributors. The final result ended up with over 100,000 lines of code. And it still involved a good number of subjects in pure mathematics: algebra, category theory, homological algebra, combinatorics, analysis, and topology. But in comparison with the breadth of subjects that appear in MathLib, it's still small. Okay. So I want to give a, okay. So first, let me just mention some common features between these two areas of formal mathematics. They're all collaborative, they're asynchronous, and they're open. And these are somehow my favorite parts of formalizing mathematics. They're very collaborative, in my experience, much more so than regular mathematics. They're asynchronous in the sense that we don't need to kind of get together in person to make progress. And somehow the interactive proof assistant ensures that there's consistency at all times. So we don't need to somehow always be on the same page as collaborators. And it's open. So certainly MathLib is open source. Lean itself is open source. And I hope it stays that way. Okay, so I wrote demo, but this is not a real demo. I'm not gonna actually change from the slides. I just wanna give a brief indication of what it feels like to work on a project like the liquid tensor experiment. And this will tie in quite well with the previous talks this morning involving abstractions and holes and sorries and admits that were mentioned in particular in Avi's talk. So let's take this piece of code. So the precise mathematics is not going to actually play an important role. I just want you to kind of get a feel for what the structure of the workflow is like. This is saying that a certain category called condensed AB, the category of condensed abelian groups, is an abelian category. If that means something to you, that's great. The main thing I want you to notice at this point is that at the very beginning, we start with labeling it as a sorry. That's a hole or a placeholder that eventually would have to be filled in. So if you think of this as a piece of mathematical debt that will have to be repaid before the project is finished. The point is that at this point, any collaborator working on a project can use the assertion that this category is an abelian category, which means that they can talk about kernels, co-kernels of morphisms, exact sequences, and so on, without actually having an implementation of the fact that it's an abelian category. Now, when we start repaying the debt, we use the definition of an abelian category, which it's a pre-additive category satisfying some additional conditions. And the key thing to note is that when we break up this first target into smaller components, the number of saris increases. It increased from 1 to 6. But at least conceptually, these targets are of smaller weight. They're somehow more tractable. And the idea is that you take each of these targets, you break it down recursively over and over and over again until you get to a point where each one is tractable and can be handled directly by one of the contributors. Okay. One of the main amazing features of working with proof assistants is that contributors can focus on individual targets that they feel comfortable with. Maybe they're experts in homological algebra and they can fill in some of these targets directly. And they don't really have to worry about some separate part of the project because the interactive proof assistant ensures that there's consistency at all times. So let me focus, let me just continue with this example by focusing on these two lines here. These are both examples, mathematically speaking, examples of existence of kernels and finite products, which are examples of limits in category theory. So after a few reductions, if you know a little bit about sheaf theory, these boil down to a certain lemma that essentially limits in the category of sheaves can be computed by looking at limits of the underlying pre-sheaves. Again, the mathematics isn't that important, but I wanted to mention that these two targets in the middle here follow from this. And at this point, this is a SARI that can very easily be handled by something from the library. Namely, it's an application of two small results, which I've written here. Okay. All right. Let me move on to what I think AI can do to help in such research formalization projects. Let me first start by giving some ideas for how it can help today. So this actually ties in really well with Avi's talk from the last session. I'm going to give two main ideas that I think would be quite nice to implement. The first is an AI collaborator. The idea is to have some system that will look at a project like the liquid tensor experiment, maybe while it's still being under development, and look at all occurrences of SARI, or all holes in the project. Try to solve the goal for each one. If it succeeds, commit the solution. If not, move on. Now, the point is that, and this is maybe the key point that I want to make here, is that such a tool can be useful even if the AI is not smart. If it succeeds, then great, we have a solution. If not, then fine, whatever, move on. Someone will get it eventually. And this can be done asynchronously, maybe as some continuous integration process every single night. We already have a few AI-based tools that solve goals in Lean. I've listed them here. And I've also mentioned that it should only attempt proofs at this point. And this is because, as was mentioned several times already, getting AI to construct objects in mathematics is quite a challenging problem, at least for now. So to make this actually useful, I think we should focus on trying to have the AI fill in proofs. Another point where I think AI can really help right now is in improving the user experience of mathematicians using the formal systems. Some ideas are develop some tools that let you search for lemmas by name, statement, or type. Integrating with large language models can help, can allow people to even use natural language for their search. And the key here is that there should be some editor integration. This was already mentioned in Johan's talk in the first day and in Avi's talk earlier today. And again, I feel like these tools can be useful even if they're not too smart. Even if I want to search for a name that's very close to a name that already exists, it'll be useful for me to be able to do it from my editor as opposed to going through to some separate website and opening a browser and doing the search that way. Okay. Of course, there are some barriers to these, namely cost is an obvious barrier. A more serious barrier is the fact that this is infrastructure that has to be maintained, and that there's a culture separation between somehow the open source or the open culture of academia as opposed to the profit-seeking culture of companies like OpenAI and yeah. My slides are not moving. Let me spend the last minute or so talking about how I feel AI can really, how interaction between AI and mathematics can really improve in the future. In general, I think that mathematics research is hard to categorize, but it can be split up into two categories: problem solving and theory building. And when we formalize mathematics, we don't just solve problems or build theories, we actually try to understand the problem solving process itself. And as again, was said multiple times, one of the main challenges of formalization is finding the right definitions. And I see a lot of parallels with what's going on in AI research nowadays. For example, these novel prompting techniques for large language models like chain of thought or tree of thought are essentially about breaking a problem into smaller components that can be handled properly by a large language model. And again, as I mentioned earlier, getting AI systems to produce usable definitions is a huge challenge. So my hopes are that mathematicians who have gained expertise in formalizing mathematics can help AI, and conversely, advances in AI can help formal mathematics become more widely accepted in the mathematical community. But the bottom line is that I feel like we need to increase collaboration with mathematics and AI. Again, this is something that's been a constant theme in this workshop, which I'm very happy to reiterate. All right, thank you very much. And that's it for me.
Thank you so much. Yeah, it's great to see how the successes of this model have influenced mathematics already, and I'm sure a lot more is to come. I just want, Alex, are you? Yes. I see you there. Good. Are you ready to present?
I am.
Okay. Well, then I'll hand off the baton to you. Thanks.
Okay. So thanks a lot to the organizers and everyone who made this this event possible. I think it's really interesting to have a lot of interplay and discussions, and this is very necessary. And now's the time to be doing it. My talk, I think, will be. Javi said his was speculative. Maybe mine's even more speculative. I don't know. We'll see. But I wanted to start by working backwards from, what should be our goal? What's the Holy Grail? Maybe the Holy Grail is that AI comes along and helps us solve the Riemann hypothesis. Well, I suppose there could be a nightmare if the way that it does it is by not allowing us to understand what it's doing, and then people like me are just spending the rest of their lives just trying to follow along with what it's trying to understand. It spits out a million lines of code, and you're trying to go line by line, trying to get some reasoning out of it. I don't know, maybe it's even more of a nightmare if its solution to the Riemann hypothesis is beautifully comprehensible and just explains everything, and then what is there left for me to do? As Adam was just saying, another potential holy grail is that AI starts making its own mathematics. It starts making definitions, starts making conjectures, starts finding patterns, not just patterns in numbers or in shapes, but patterns in reasoning that we haven't even conceived of before. So maybe 100 years ago, if someone started talking about infinity categories, people would think they're nuts. Of course, now that's something people make a living thinking about. Just another example of something that's kind of nuts. And until recently, I was the editor-in-chief of the journal Experimental Math, where we really try to find the instances where something is outside, where some new pattern has been observed, but it's outside the realm of the way people are thinking about mathematics. So just one example is, people looked at Fourier coefficients of the J invariant elliptic curves, and they found these very surprising correspondence to dimensions of irreducible representations of the largest sporadic simple group, the monster. And so this became known as the moonshine conjecture, because you'd have to be absolutely, drunk on moonshine to think that there really is any such relation. And of course, eventually, people from vertex operator algebras proved rigorously what was going on here, and this won Borchards a Fields Medal. So this is the kind of thing. Now, human beings already do this, but if AI is capable of doing this kind of thinking, it could just run away from us. So that's another, holy grail or a nightmare. Certainly an interesting scenario. But at least as far as I can see right now, either of these scenarios are science fiction, and who knows what will happen in 6 years, or maybe at the pace things are moving now, 6 months. But a much more modest proposal for a holy grail would be just that AI assists us in theorem proving, much more like what Adam was just saying. So what would it take? And of course, presumably, in order for it, if it can solve the Riemann hypothesis or make its own definitions and conjectures, it can also assist us in theorem proving. So that, I would say, is a precursor to these other potential eventualities. So, the workflow of a research mathematician, you have some idea, I think this can be used to prove that. I think I can solve this using these techniques. You have some kind of big picture, and then that's a theorem or maybe a bunch of theorems. And each of those theorems breaks up into propositions, and each of those propositions breaks up into a lemma. And at each scale, you have some ideas. Maybe you have some standard techniques you want to apply. Maybe you have a new novel technique that you want to bring in that hasn't been used in this subject before. So standard, non-standard techniques, some work, some don't. And you sort of rinse and repeat at every scale. And then eventually, somehow miraculously, you get a theorem at the end. And a lot of the little steps here do feel like they could be automated in ways that in other labs in sciences, we have labs of PhD students and postdocs. This really doesn't work in mathematics. Mathematicians, I don't give a PhD student a little lemma from my main theorem to see if they can actually prove it. I give them their own theorem to try to prove, and so that they learn how this whole process works. But this is where an AI assistant who learns what the Cauchy-Schwarz inequality is, you can say, okay, try Cauchy-Schwarz in these variables, try exponential sum estimates in these variables, and see how far you get. And that would really speed up my workflow. So that's something that has potential applications. Now, of course, okay, if AI is going to do this for us, it needs to train, and it needs to train on large data sets. And the question is, large data sets of what? And so here's my sort of very speculative conjecture. So large language models trained purely on language alone will not, my conjecture is that they will not by themselves reason at professional math level. So we've seen that they can take SAT tests, they can solve all kinds of problems, surprising ones. My evidence for this is that we have lots and lots of human beings, and almost all of them acquire language automatically, but the kind of training that it takes for people to even begin to contribute to advanced mathematics is often, a 4-year bachelor, a 5-year PhD program. Now, there are other things that LLMs that also require this kind of rigorous training, and LLMs are successful at solving. And but those things are often statistical. And at the end of the day, a rigorous mathematical theorem is not statistical. There's statistical processes determining how to state the definition, what kinds of theorems you would like to say. But then at the end of the day, there has to be a proof at the end. The counterpoint to this conjecture is that there are people much smarter than me and putting a lot more resources than I have into actively disproving this conjecture. So people at OpenAI, at Google, lots of other places are really pushing the idea that if only LLMs had enough training data of the right kind and enough transformers, enough parameters, they would reason. This is closely related to issues of alignment, which is a whole other direction that I won't get into. But okay, so this is sort of a conjecture. And, even if the AI could, with natural language, solve problems, it tells me a natural language proof of the Riemann hypothesis. How do I know that it's right? Now I'm sitting there not only trying to understand what its ideas are, but just maybe it's complete nonsense. And maybe I'm wasting my time. So is there a mechanism, some kind of certificate that what it's done is correct? And so a second conjecture is that the path towards AI helping us with reasoning is through an adversarial process. It's not just tokens, but it has to go through something like an interactive theorem prover, like Lean, Isabelle Koch, the kind that we've been hearing about all week. And so if that, if you believe that conjecture, if that seems plausible to you, here's a suggested holy grail. And again, this is something lots of other people have discussed. So maybe the prompt is natural language. Maybe it goes to GPT 1984. That talks to Lean back and forth, something like Lean, and iterates on, well, do I think this is right? I have some ideas. Like the statistical models are really good at telling you which direction might work. But then you need to know, is it really a theorem? Does this approach actually work? Does it actually get you something? So that there's a loop there. And then the response could be natural language. Here's what I think you should do with this lemma that you're trying to prove. Let me recommend Cauchy-Schwarz in variables 6 and 8, but not 1 through 5 and so on. And together with, if you want to check under the hood, there could be a formalized certificate that what it's saying it's not hallucinating some nonsense. It's actually that really is a proof of the lemma that you had in mind. So you can say, okay, great, that lemma is taken care of. Let me see what else. Let me move much more quickly through the search space of mathematical moves, trying to prove a theorem. And so for me, the real question is how to train this interaction from perhaps natural language to Lean and back. And, things like GPT, BARD, et cetera, these are trained on terabytes of whether it's bytes or tokens or lines of text. You need massive, massive data sets for these things to get really good. I think if you put together all formalized libraries that exist today, we have on the order of 10 million data points, whether that's, again, lines of code. Do you want to feed goal states in the next line in the proof? Is that what it should learn? Should it be natural language statements and the corresponding formal line? Should that be the pairs that it's trying to learn? So all of that is kind of open question, and there's lots of activity that needs to happen here to answer those questions. But whatever it is, we need we need orders more magnitude of data as far as I can see. And so this is a third conjecture, that the current rate limiting step for having this get really good is producing orders of magnitude more high quality formalized mathematics. So, how do we produce more? Well, it's hard. It's actually hard, especially if you go beyond the undergraduate or graduate level. Modern mathematics involves, as we've already said, has been said many times, interactions between different subjects. And this is what's amazing about the MathLib library. It's a huge library, which is itself a bunch of libraries, and they all talk to one another. So just another example of something you might try to formalize. Elon Lindenstrauss got the Fields Medal for his resolution of the arithmetic quantum unique ergodicity conjecture. For that, you would need, some differential geometry to get to your mathematical physics. You need representation theory. You need the theory of algebraic groups over the Adels. You need Hecke operators. You need a million different things that all get developed in different graduate courses, all working together to prove one big theorem. And so that if we can get those kinds of interactions across one another, we have some chance of success. Let me also say that we're getting better and better. Yes, it's difficult to produce high-level formalized mathematics, but actually we're getting better and better at it. Here's just 3 examples where a formalization of an annals paper took 2 years, and then the next annals paper took only 1 year to formalize, and now we have a paper. This is Tom Bloom's solution to the Erdős-Graham density conjecture about Egyptian fractions, these unit fractions, where the formalization came faster than the referee report. And so, in that sense, things are speeding up. In another sense that things are getting better is that pretty early on, people were able to, so Jeremy Avigad led a team that managed to prove the prime number theorem. Well, defining prime numbers is quite easy. These are elementary objects. The prime number theorem is a difficult statement about those things. And we were already capable of formalizing that. More recently, we could prove simple facts or just state the definitions of very complicated objects like perfectoid spaces. And of course, as we just heard about the liquid tensor experiment, now we can prove really difficult facts about really complicated objects that synthesize large libraries across different branches of mathematics. So we're really getting, as human beings, we're really getting quite capable at these things. But again, oh yeah, let me point out one other thing, which is that when you get the API right, there are certain situations where a formalized proof can really look exactly like a human proof. So this is, don't read anything that's there, but this is just an example of, what is it, 35 lines of code, which, so this is from a formalization of mine with Heather Macbeth, that if you take a locally compact Hausdorff space, topological space with a discontinuous group action, the quotient of that will also be Hausdorff. This is the kind of thing that, you know, first-year graduates or advanced undergraduates do. It's a little exercise, but almost every single line in this proof, in the formalized proof, is exactly the same as the human proof. So, so again, things are getting better in the ability to formalize, but it's still, I think, difficult to go from, you know, we won't get a trillion lines of code just with human beings getting better and better at things. And so let me point out this very interesting paper of Christian Szegedy about auto-formalization. So before AI should assist us with solving new problems, at least it should be able to, if it's going to go through this formalization process, at least it should be able to independently solve problems that humans can already solve. So this is the question of auto-formalization. I'm going to run out of time, but let me just mention a few things. I think these have almost all been discussed already. So there are lots of, this is really something that people are getting into these days. So let me just end with what I kind of see, you know, maybe the better we get at human formalization, the better we'll get at auto-formalization. That is a loop. That itself can feed into AI actually assisting with theorem proving through lean, and then eventually maybe we'll go into these other directions. So if I were, you know, trying to determine where I want to put my resources, maybe on the left-hand side of this is where I would spend some energy. So let me stop there. Thank you very much.
Thank you very much, Alex. So yeah, we've covered a lot of ground. So let me turn to questions. So let me start with a question that was asked of Javi. So and then I'll start to turn to general questions in a moment. So Javi, what properties of these physically inspired neural networks set them apart from other approaches? How are they allow you to do things that couldn't be done before?
So the honest answer here is I don't fully know, and nobody fully knows. What I feel maybe an advantage is the high degree of nonlinearity, meaning the way you work, let's say in finite elements or there was another question asking about finite elements, is that essentially you have your basis and then you write a solution as a linear combination of that basis, and then you sort of minimize or solve a system or whatever. Whereas in the, let's say in the neural network approach, your basis is a highly nonlinear composition of some basic functions. And I think this high degree of nonlinearity somehow leads to a better approximation in the sense that you require less terms, you require less effort to be close enough from a solution. This is my feeling. I can't prove a theorem as to that being right, but that's my feeling as to why they work better, and they can explore regions that are far away and may take like an absurdly amount of, let's say, of modes or of your favorite basis functions to get there. So that's kind of my take. But there is no rigorous mathematical theorem about this, other than a few cases which are like soft analysis.
So let me turn to a question for Adam next. So how does a project of Lean, how does it interact with existing incentive structures in mathematics? So, you know, to get tenure, you want a paper in a fancy journal, but if you're involved in a collaborative project, there's more of a group contribution, and it's harder to assign individual credit. So what does this mean for the development of these resources? And maybe how does the mathematical community have to adapt in order to reflect modern modes of scholarship?
That is a very good question that I don't have an answer to, unfortunately. I mean, I think this is a huge issue that needs to be addressed as if formalized mathematics is really going to become mainstream. With the liquid tensor experiment in particular, we were somehow quite lucky that Peter Schulte was involved and kind of popularized the whole thing. But I don't have a good answer, unfortunately. Yeah, maybe Alex has some ideas along these lines.
Alex, do you want to take a crack at this question?
You're muted, Alex.
Sorry. Yes, it's something I've been thinking about a lot. There are a lot of young people who are spending a lot of time doing very, very difficult, technical, high-level work that the community should reward, and yet the mechanisms for rewarding that work don't yet exist. So you can try to wait for the mechanisms to come around and for people to say, oh, I've formalized 2,000 lines or 20,000 lines or 200,000 lines of code in Lean, and that should count for 10 papers, or you can do this kind of arithmetic. I see that as a much more difficult path towards recognition. What I would say is the Lean community should meet the math community where it already exists. So at the moment, when you have a really big, like liquid tensor experiment, some big project, okay, that's maybe an order of magnitude higher project than a lot of the day in and day out projects. But you formalize something really nice. You've already, if it's in MathLib, it's already published in the most reliable journal on the planet, namely MathLib. So MathLib itself, it has maintainers. The maintainers are effectively editors. And the style of the journal is kind of like a PLOS. If there's a public library of mathematics, then that would be something where if it's correct and it's new, then it should go in, right? That would be that kind of journal. So in that sense, MathLib is the editors are checking if it's correct, if it's new. I mean, they don't have to check if it's correct because Lean checks that it's correct. You have to check that the definitions are stated as you would think they should, which is highly non-trivial. We ran, just a little anecdote, we ran a special issue in Experimental Math on interactive theorem provers. And I thought, as editor, this is going to be the easiest job in the world. I just asked people, can you check, Lean has already checked the correctness, or Isabel, or we had submissions from all kinds of interactive theorem provers. But it turns out that the referee still has an awful lot to do because it's rather non-trivial. And in some cases, there were formalizations that needed to be sent back to the referee to change a definition, which actually, it ended up proving something which wasn't what they advertised as having proved. So that's itself non-trivial. But MathLib is already a journal of the highest order, and you have a complete public trail. As Adam said, everything's open. So you know who did what, over what period it was contributed, what the referee report was, because as the maintainers go back and forth with a pull request, you see that they suggest some simplifications here, they suggest some modifications there, and then the final version goes in, and that could be a publication. So I would advocate to the Lean community to start an actual math journal associated with MathLib. And when there's a very significant contribution to MathLib, that should come with, associated with that should be a paper that points to the formalization. And there could be a meta discussion, these are the things we found difficult, these are the lessons we learned along the way of formalizing this fact, so that those things can begin to get counted in the standard math way. Now, maybe in the future, there's some mathematicians come around and find a new way to reward research being done in this direction, especially by young people who, a lot of this work is being done by young people. They're going to be evaluated for promotions and for tenure and for prizes and all these kinds of things. And it would be great to have this work recognized because I think it's very important. It shouldn't be just papers. And right now, as I understand it, some of the best Lean work is going into computer science proceedings, which is great. But again, pure mathematicians don't really have a broad awareness of what that means and what's a good journal, what's a good proceedings, what's not, what's a good conference. So there's some discussion to be had in this direction.
Maybe I can just add a couple of points to what Alex just said. Concerning verifying definitions, Johan mentioned this earlier in the week. What we did in the liquid tensor experiment is we added a bunch of examples that somehow illustrate that the definitions that we formalized behave as a mathematician would expect them to behave. Like, for instance, the X groups that appeared in the project, we proved that they form a universal delta functor. So, you know, that should be as convincing as possible, right? Now,
especially when the theorem is that something is zero.
That's right. Yeah.
That scares people, yeah.
And also, Heather mentioned this in the chat, so I just wanted to mention that when we say lean, we should really be talking about proof assistance in general. Yeah.
I want to give Javi a chance to talk about the incentives in the mathematical sciences and what are the things that we as a community need to do to make sure that this scholarship is recognized and people can develop in the profession by doing these kinds of work.
Yeah, I think what Alex suggested, I think it's a very good idea to sort of, you know, come up with a journal from the theorem provers community and sort of highlight it there as well and sort of like make it interact. But maybe, you know, being more aware of what computer science conferences are and like for cases like this from the math community, this may be some homework that let's say more traditional mathematics or more traditional departments that are maybe not so up to date with how things work in this sort of different or new fields. Maybe that's something that departments should be aware and should take note of. So it goes both ways in the sense that the let's say more traditional math people should put more value and look more into that. And let's say the more modern mathematics should also try to bridge the gap and come up with, let's say, more traditionally minded solutions as a new journal.
So I know that Alex talked a little bit about large language models in the context of his grand vision of how these things would fit together. Would Adam or Javi like to talk about these things, or would you? Yeah, I'll give you a chance to respond to some of the things.
Sorry, could you ask that again?
So there's been, of course, large language models have gotten tons of research attention. Do you see those things as influencing the way work is done in the areas that you're active in?
Yes, I definitely think so. So for instance, in this little demo that I went through, I explained how, you know, definitions kind of, we break down these saris into smaller and smaller ones and so on. And this process is essentially governed by the definitions themselves. Unfortunately, I didn't have time to mention this in the 15 minutes, but I feel like as large language models or AI in general becomes a more useful assistant, we'll keep that in mind when we're building mathematical definitions and abstractions in ITP or even on paper in order to somehow make it more amenable to be, for the AI to be useful. I think that's quite interesting, how to write down a mathematical definition that's interesting as a mathematician, or interesting mathematically, but also do it in a way that where AI can be helpful. I think these are very interesting questions.
I think, I mean, my take on this is that LLMs, or I think this is one of the biggest things that LLMs have achieved, is to raise public awareness of this kind of science. I think now everybody knows what ChatGPT is, and to some extent, what is an LLM, let's say, you know, compared to 5 years ago. So I think that's an opportunity for the mathematicians and the scientists in general to try to sort of educate like the general public about what is math, how does it interact with these kind of things, does it have a future, is this the future of science? And I think that's a big opportunity because it's difficult to talk to people about math. But now I think this is a proxy that one could try to use to sort of advertise more math or explain better the science or just reach further away. And I think this is now a big opportunity in that direction.
So sometimes breakthroughs in mathematics are driven by cutting across fields, having an idea in one area that's well known in a certain community, translating it so it can be used in another subdiscipline. Do you think that this is something that artificial intelligence could help to encourage, mediate, or do you think that this is a uniquely human approach to solving problems? Maybe Alex, I'll let you take the first crack.
There are a number of things that I've seen that I really thought were uniquely human, and then I see computer systems doing them. So yeah, I sort of envision, especially if we really have this AI assistant, maybe the AI isn't doing its own, maybe it's not proving things we don't know how to prove, maybe it's not necessarily making its own mathematics, but it can really be a resource in the way that the experimental mathematics journal is meant to be a resource for people to put out something where I really don't know where this is going. Where could this pattern, what could it possibly have to do with? Especially if it knows, Lean or some other theorem prover, if there are these huge libraries of mathematics, you can say, this is a pattern that I'm observing. Could you tell where this pattern is coming from? And it might be able to suggest some structure. I mean, if these statistical models are really good at seeing patterns, then yeah, I see that as being a really potential big benefit. Of course, it remains to be proved, but.
Adam, do you have any thoughts on this?
I mean, my favorite analogy in mathematics is the analogy between function fields and number fields. And right now I cannot imagine a large language model or anything like this coming up with this analogy. Although, it's not inconceivable because somehow I feel like this analogy came about because people saw patterns in number fields and patterns in function fields and that look very similar. And in principle, these are patterns, like Alex was saying. So maybe. I think, once this workshop is over, I'm going to go play with ChatGPT and try to ask if it can come up with some analogies in math and see what happens. But I don't know.
So yeah, I mean, I definitely do see AI helping a lot in the sense of discovery and observing patterns and extracting some suggestions or even suggesting some theorems. This is also tied to Jordi's talk the other day. I think it is quite useful, and it can reach beyond what we can conjecture in some senses. So I think in the sense of exploration, it's something that it's already happening. So that's definitely going to be a thing in mathematics in many fields. I mean, this is at least what I would expect. Now, whether it can solve everything and do everything, I don't know. But certainly, as some kind of assistant or as a helper to discover new things, and then maybe a human or Lean or a combination of all of them, or maybe even backflowing and sort of running several iterations of this, I would expect it to be likely to happen soon.
So I have a question for Javi, but I think I can generalize it so it makes sense for Alex and Adam. So in your presentation, I was left with the impression that the results that you're obtaining weren't so sensitive to the specific equation you were working on. Maybe that's because you suppressed all the hard details for the benefit of algebraists like me. But do you think that there's something, is this impression totally incorrect, or do you think that, yeah, so maybe you can talk about this aspect of the work.
Yeah, I mean, I don't claim that this is like something that will solve every single PDE problem in the universe, because everything requires its own little details. But from what we were observing, the discovering phase was not tied to a particular problem. Like sometimes you can use a lot of information that you have gained through mathematical understanding of how things work and sort of what are the interesting regions and where to look at and what is important, what is not important. Our experience with AI, which is, again, relatively reduced, was that we didn't have to supply that much of a priori knowledge of the PDE or of the field. Of course, if you supply it with more, then it will perform better. But our understanding was that, and this is something that remains to be explored, and this is something that we don't see quite well why it does this way and not the other way. Our understanding was that it was sort of light on the prerequisites. So I can't really explain why it does these discoveries, but it does them. So this is something that we are sort of, and by we, I mean all of us, should be in the process of understanding better, because it's really on its infancy. And now it's sort of driven by the outcome, in the sense that whenever I get these kind of similar questions, my answers are usually, well, I don't know why, but it seems to work and it seems to outperform whatever I tried before. Do I understand it? Not yet, but this is the direction of, like, you know, it does have a potential to become better, and certainly with more effort, I am sure we will understand it better and so on. But at least I'm impressed by the kind of things that AI can do at this point, even with a caveat that we know very little about it for now.
And so I want to spin this by asking, to what extent can engagement with machine learning techniques or proof assistance, can they drive generalizations as you find certain structures might apply across related problems? Can the machines get us to do the things that that we naturally are inclined to do as mathematicians? Look for general principles behind things. So maybe Adam and Alex.
Yes, I definitely believe that this is one of the strong points of formalizing mathematics. Is it really makes you find the right abstraction that makes the formalization easier. But at the same time, in practice, it seems that the right abstraction is also the right abstraction mathematically. That's what I would say about that.
Alex, do you want to weigh in?
Yeah, just to add, I think pedagogically, there are a lot of times where you talk to a student and they say, why do you need this generality? You know, why are we working? Why can't I just work with matrices? Why do I need abstract vector spaces or something? And I think when you prove a theorem in a theorem prover, you often actually, if you're in the more specialized case, you get stuck trying to use things that are special to that case. And if you could only see the more general picture, it actually makes it easier to formalize things that are more general than things that are more specialized. So you sort of you start thinking like, okay, but really, what's really going on here? Which is something mathematicians ask all the time. Usually we ask it pedagogically. No, we really actually want to understand, not just pedagogically. We actually want to understand what's going on. But then we'll go back to our models. And I have a matrix in my mind, in my head, or something, or I have a linear vector space, but I'm not thinking of I'm thinking of Rn instead of something abstract. But when you go to formalize, you really start to feel, oh, wait, I don't need the real numbers. I don't even need a field. Maybe this is just so you start to appreciate more what abstraction is for. So that's something where the more formalization happens, the more you sort of recurse backwards into what's really driving this theorem. And then it becomes really relevant, because now you can apply this theorem more generally, and you certainly don't want the same proofs, the same ideas getting reproved lots of different times, as opposed to quoting the same structure once and for all.
I think that's a very good point. That it really forces you to extract the ideas, and I think that's a huge positive of formalization.
So in the chat, which I'm not sure everyone can see, there's been a lot of discussion about analogies between geometry and number theory. Alex, is there something you'd like to just say to the group about analogy and how it's a driver for discovery and conjecture, and maybe what it what role it has in the brave new world we're entering in.
Sure. This was just a reaction to Adam asking, does ChatGPT actually know anything about the analogies between number field and function field settings? And so I just asked it, what would be the twin prime conjecture in the function field setting? And it gave a perfectly, 3 paragraphs it probably read it in a paper somewhere and just regurgitated what it read. But mathematicians have already talked about analogies between function fields and number fields. And it accurately, I didn't read it closely. I don't know how accurately it did this. But at a glimpse, it's stated the right things that I would also say are the analogies.
And so did it give a citation?
There's no citation, and there's no verification that it's not hallucinating some nonsense.
Yeah. So, Adam, do you want to respond on the issues of analogies and how these techniques?
I mean, I think analogies are very powerful in mathematics. Somehow, they're one of them. I see them as one of the main drivers of progress somehow. And I think in relationship with artificial intelligence, this would really, I think it's related to the question of how to get machine learning tools and artificial intelligence tools to come up with constructions and definitions, because I feel like often in math, the definitions we write down are motivated by some sort of analogy. And like others have said before during this week, this is a very hard problem for AI, and I'm certainly not an expert in AI, so I can't really comment on that, but yeah, I don't know what to say beyond that. Yeah.
Are we allowed to ask Talia to say more about what she wrote in the chat?
I think I'm going to make an executive decision and say, Talia, do you want to say a couple words about the discussions that, if you're available?
Oh, can people see me? Sure. Sorry. I was just talking a lot because I get excited about this thing because it's just one of my major interests right now. I've been thinking about this topic of like analogies a lot and how we can get machine learning tools to pick up on them, because you can get kind of classic AI tools to pick up on them if you kind of program it to search for a class of relations that relates different things, and you can adapt proofs across those, and that's awesome. A lot of the neural tools are extremely bad at this. And so even like a slight change in how you phrase something means that, it won't be able to pick up on the fact that these proofs are related to each other, unless there's some really obvious, like, kind of syntactic proxy for this. Like I think one of the reasons that this is easier in like natural language is that, something being used in similar contexts is like a good enough proxy for it to relate things. And sometimes in mathematics, if people have named things similarly, like that might be enough, but often it's really not. Like often there's a much more interesting like notion of analogy that has some complicated semantic structure. And I think right now there are some architectural limitations that make it like hard to learn these kinds of relations effectively, but I also think they're resolvable, and I have like great hope for that over the next 5 or 10 years. So this is something I'm happy to talk to people more about anytime. Yeah.
Thanks, Talia. So I want to raise a question that's in the chat. So there are some areas like low dimensional topology where visualization and geometric insight really drive progress. And so is this just an area where we're not going to be able to formalize, or is it present unique challenges to achieving the proper formalization of arguments? So what role does geometric intuition and visualization, what does it mean for these brave new approaches to mathematical problems? Maybe, Javi, why don't you go first?
Yeah, no, I mean, I'm not an expert in this field, but maybe the issue here is to come with, a correct standard or a correct way of defining things when it comes to the verification. But on the other hand, I see this as a good thing, because there have been issues whether a proof by picture is correct, and this, let's say, not so conventional not so conventional papers and not so conventional results that have been going on for a couple of years. So maybe this is an opportunity to sort of just go on, formalize everything, and then there is no questions or no doubts raised about any sort of validity of the proof whatsoever. But I do think it's a challenge to come up with like a good representation or a good structure to formalize this kind of results. Maybe some of the low-dimensional topologists can chip in or say something. I'm not so familiar with the idea.
So, Adam, do you want to comment on the challenges of incorporating visualization into formal arguments?
Maybe I can first give a practical answer, and is that very recently in Lean, in MATLAB 4, we got proof widgets, which lets you visualize some part of a proof that you're working on. Say, we don't have anything in low-dimensional topology, but we have things like commutative diagrams that let you visualize, say, a diagram chase or something like this. And in principle, you know, there's no reason why it can't be applicable to, well, I don't know, I'm not an expert in this field, but it would require a lot of work to prove things formally, but I think the infrastructure for at least visualizing things while working on something formal exists. It needs to get better, of course, but I think this is work in progress. Now, maybe from an AI perspective, there was a talk, I don't remember if it was a talk or it was during one of the panels earlier in the week, about getting artificial intelligence to visualize things in order to develop constructions. And I don't remember exactly the details, but maybe that's something to look back at the recordings. And, yeah.
I'd like to ask one question before handing the baton to Alex. So one of the criticisms of Euclidean geometry as done by the Greeks is it implicitly relied on pictures and wasn't quite the paradigm of reasoning. Has that been completely formalized? And you know, is there some loss in terms of the ability to visualize what's happening?
So a student of mine has actually just formalized book 1 of Euclid's Elements using Avogad's axioms. So in Lean, in Lean 4. So yeah, you can do all of, you have to add a bunch more axioms that Euclid sort of diagrammatically overstep the bounds of the axiomatic system that he set up. And of course, we have the modern understanding that you can't define things like points, lines, and planes. These are undefined terms, they're types, and it's really the interactions between those that are what makes a geometry. If I can just about your earlier point about visualization in general. So I think one of the, is it correct to say that one of the least developed undergraduate topics is complex analysis in terms of the kinds of things, the kinds of, you draw this contour and, here's the location of the residue and you just do residue calculus and you get all your answers. So yeah, it's hard, especially we human beings have such a highly developed visual cortex. Even the fact that we write our formulas on even if it's an algebraic statement, when you write it down, you understand it better somehow, having seen it, even though it's just an equation. I mean, this is the miracle of algebra, is how it manages to compactify very difficult ideas into something that's manageable by a human being. So yes, I think visualization is something that human beings are really good at, and we need better ways for AI to do it. Actually, Christian Zegedy's auto-formalization paper said we should just feed it the JPEG of books, mathematics textbooks, and try to have it take those mathematics textbooks. It's all written in natural language, of course. You convert that to convert the JPEGs, including somehow the pictures, into formalization. And yeah, I don't know how close we are to that. That seems farther off to me, naively.
So Some of the comments cite scaling challenges. Of course, there's getting the computer resources to scale the computations, but there's also the human resources. One of the things that Alex mentioned was an exhortation to have more humans involved in formalizing proofs, and that as that activity becomes larger, there'll be a lot of benefits. So can you talk about the scaling challenges that you see in the areas that you're working with, and how are they, what are the things that the community can do to address them? So maybe, Javi, do you want to go first?
Yeah, I mean, usually my projects are relatively small or moderately small that, let's say, a group of let's say, collaborators can handle this. But I certainly do see the challenge whenever I would try to work with libraries and, like bigger things. And it's tough. It's tough because, again, kind of back to the point of like what we discussed before, there is very little reward the way the system is set up now. So then it's hard to convince somebody to, just devote a lot of their time into growing this or even better, like even worse, curating it and obtain like zero reward out of it. And if we talk about young people, then you're not doing them a favor the way the system is set up now. So I think that's quite a challenge, and I think that's something that should be addressed if we want to move forward and scale this up. So yeah, just kind of resorting back to the previous point of how should we value this and what's difficult about it. So.
Adam, can you comment on the scaling challenges and what are the things we can do to get more people involved?
Yes. So somehow one of the most tedious things about formalizing mathematics is, having to deal with a bunch of little side conditions like, some very trivial inequality or very trivial diagram chase or things like this that on paper you would never write down. And somehow my hope is that AI or better automation, namely symbolic AI, would make those issues disappear somehow. You mentioned, computational issues. At least in my experience, there are still computational issues with formalization in that you pretty much have to split up your proofs, at least in Lean, into smaller pieces, because once they get, 100 lines long, it becomes completely unworkable. The computer slows down, your fan starts spinning, and it's just terrible. So just from the practical reason, you kind of have to split things up. Sometimes when you're building lower level theories, that's okay because you want small individual lemmas that are reusable elsewhere. But as you get more and more advanced into more serious mathematics, that's not the case. In my experience, there were situations, for example, working on the Liquid project, where I wanted to write a proof that's 300, 400 lines long that has kind of one-off constructions in the middle somewhere, but I had to split things off just because the system was too slow. Again, I think automation can help with that. If there was some automatic way of taking this one-off construction and telling the system, okay, go split it off so that I can reuse it and don't recompile it every time I change something, that would be great. We're not there yet. That's an engineering issue, I think. But in terms of scaling to the number of people using formal mathematics, I think what Javi just said, there's the incentive issue and there is the learning curve that I think AI would help. But I think beyond that, I think those are the two main issues.
Alex, do you want to address the scaling issue?
Yeah, well, as Adam just said, the issue with, maybe this is a technological issue that can be somehow overcome, but absolutely, I've run into situations where the thing about working with an interactive theorem prover is you write a new line of code and it updates the new goal state. And so if it takes it 5 minutes to update a new goal state, you just can't work that way anymore. And so with Lean 3, after 1 million lines of code, it was really starting to be a victim of its own success. And so there was this big port to Lean 4. Maybe Lean 4 can handle 10 million lines of code. Do we need Lean 5 to handle 100 million lines? How do we get to actually very, very large systems? There's a whole technological issue there. Even if AI was good at producing more formalized mathematics, it might be a victim of its own success. So yeah, there's some very serious challenges just up the road.
So my schedule says that we're going to have a break at 1:10. And for those of us on the East Coast, it's probably time for lunch. But even people on the West Coast need a break from time to time. So I'm going to thank our panelists. Thank you, Alex, Adam, and Javi for telling a wonderful story and helping to inform where things are going. And thanks all.
Thank you.
I have to leave the workshop now, but it's been absolutely fantastic. Thank you to everybody who's organized it. And I particularly love the quality of the discussion sessions. When you have 3 experts discussing, as we have just now, that's so much better than when you have just scrappy questions after a talk and everyone's rushing for coffee. It's been really terrific. Thank you, everyone.
Hi, everyone. It's 1:30 Eastern, so welcome back. We are about to begin our very last panel of the workshop. So before I hand it over, I'm just going to remind everyone quickly, please submit your questions on Slido. So you can do this by going to slido.com, typing in AI for Math 23 in that blue box, and then send us your questions, upload other people's questions, and we'll do our best to include them in the discussion. So now I'll hand it over to Heather Macbeth, who is moderating the next session.
Thank you, Sam. I'm Heather Macbeth. I'm an assistant professor of mathematics at Fordham University. And I want to start this session just by introducing each of our panelists and having them giving them a chance to tell us about themselves and also the institutions or professional societies that they represent. So I'll get them to tell us about the missions of these societies and also their activities. Let's start with Gunnar Carlsson. Gunnar Carlsson is an American mathematician working in algebraic topology. He is known for his work on the Siegel conjecture and for his work on applied algebraic topology, especially topological data analysis. He is a professor emeritus in the Department of Mathematics at Stanford University and serves on the American Mathematical Society Council and on the Committee of Science Policy. Gunnar, over to you.
So good morning, or good afternoon, I guess, back there. Yeah, my career started out as a pure mathematician, more or less. Did that for the first 25 years. At Stanford, around the year 2000, started to work on more applied areas. And at that time, people were talking a lot about big data. And so I spent the time developing methods, topological methods for doing machine learning and data analysis. Over time, that's turned my career a little bit. I've retired from Stanford and have been doing startups. I'm doing one right now, in fact. And also the work has changed. So I've, in the last 5 years, become very much interested in artificial intelligence, and particularly how mathematics can aid artificial intelligence. So I'm representing the American Math Society, which was founded in 1888. It's the Association for Professional Mathematicians, both academic and non-academic. It represents the interests of scholarship and scientific research, and to an extent, the teaching the more advanced parts of mathematics. And it is an advocate within, in DC and in Washington for, funding of research-related aspects of mathematics. The activities include the support of meetings. So there are numerous sectional meetings around the country. There's doubtless one near wherever you are. There'll be one within driving distance at some point. Additionally, though, there's the marquee meeting, which takes place in January of every year, which is the joint meetings of the societies. And so those meetings, it's run by the American Math Society, but other societies, including SIAM, are often represented and have a role in running those meetings. The society has partners, so SIAM is one, American Statistical Association, but many others, including the NSF-supported institutes, MSRI, and American Institute of Math, as well as others. Other partnerships include the Association for Women in Mathematics, the National Association of Mathematicians. So the AMS often will fund activities, say in these institutes or at other places, and will work together with these partners on the joint math meetings, JMM. The Society publishes a large range of journals. So there's the flagship one, which is the Journal of the American Math Society, which is one of the highest profile journals in the subject. But additionally, the transactions are more frequently, in a journal that comes out more frequently. The Bulletin which publishes not so much mathematical papers per se, although some of that, but papers that kind of an expository nature that describe interesting topics or interesting trends within mathematics. And then also the notices, which is more describing when the different events happen and so on. Large range of these journals. Some of the journals are done jointly with other societies. The society also sponsors, and based on donations, a number of prizes in mathematics, and also the AMS Fellows Program, which recognizes people who have had very productive careers in research mathematics. They also supply or have constructed some resources. So there's MathSciNet, which is sort of a search tool for finding mathematical papers that have appeared, in fact, going quite a long distance back. It's extremely useful, and what's extremely useful in particular is the fact that they have created a subject classification. So the mathematics is there's a taxonomy of it, so to speak, and you can dig into algebra and then subparts of algebra and so on. It's a very useful resource. And also Math Jobs, which is sort of a clearinghouse for jobs in mathematics, and that has been extremely useful over the years. It's it makes it very easy for both the people doing the hiring and the people applying for the jobs to find out what's available and who's available out there. So I think I'll stop there.
Thank you very much. Certainly, the AMS reaches into every aspect of our professional lives, as you reminded us. So next, we have Suzanne Weeks, who is here representing the Society for Industrial and Applied Mathematics, SciAM. The SciAM community is made up of applied mathematicians, computational and data scientists, engineers and scientists. Through publications, research, and community, SciAM builds cooperation between mathematics and the worlds of science and technology, and fosters the development of applied mathematical and computational methodologies needed in various application areas. So Suzanne holds a professorship at the Worcester Polytechnic Institute. Susie, are you there?
I'm here. Thanks so much, Heather. And thanks to you and all the organizers for inviting me and for SciAM to be part of this program and part of this panel. And yes, as Heather has already said, so I'm from the Society for Industrial and Applied Mathematics, SciAM. And from its name, you can see that our focus is on the application of mathematics, or applied mathematics as a very broad field, and that we include industrial piece to it, because a significant portion of our members are mathematicians or scientists or computer scientists, if you will, physicists or engineers who are practitioners of the craft in industry. And you can define industry as government research labs, or in the government itself, in the private sector nonprofit. And it could be about 70 to 80% of our members are from academia, right? So that's a space that we're familiar with as well. So yes, we have about 14,000 individual members, and we have, and we're in over 100 countries. We have other 400 institutional members who, take our journals and all these sorts of things. As far as SciAM goes, we're younger than the AMS. We just turned 70 last year. We incorporated in Philadelphia in 1952 as a nonprofit organization. And our goal is to convey and exchange mathematical knowledge, engaging professionals who can, let's say, leverage mathematical theory and computational work for practical, industrial, or scientific use. And we do that, our goal is to advance the application of math and computational science and engineering, industry, science, and society, and of course, math for its own sake, and to promote the research that will lead to effective new techniques and computational methods, right? And of course, we provide the media for exchange of information and ideas among mathematicians, engineers, and scientists. And so Gunnar has mentioned many of the ways that AMS provides that forum, and we do similar things. So we publish 18 of the top journals, I dare say, in applied math and computational sciences, We have an undergraduate research online journal. We publish wonderful books, and we have a nice, broad, accessible journal, the SciAm News, that many of you probably already read online or you get in a paper form. And I have some nice articles, AI related articles from SciAm News that I can share maybe on Slido or something later that are related to AI. So as I said, our membership runs to about 14,000 individuals. We have over 200 student chapters all over the world. And SciAm organizes itself not just in sections, which are geographic regions, but uniquely in activity groups, right? So that goes by interest, whether your interest is in analysis of partial differential equations, computational science and engineering, dynamical systems, uncertainty quantification, optimization. So we organize that way. That's one way we partition our set of members. They choose to belong to an activity group or not. And most of our conferences have those themes of the activity group. So for example, last week, we just had our conference in financial math and engineering. The week before that, we had our conference in optimization. 2 weeks before that, we had a conference on dynamical systems, and we have a conference on controls, mathematics of control and systems coming up in a couple of weeks in July. Let's see, I'm trying to think if there's more to say or whether I've gone over my time. Maybe I can move on, Heather, and have someone else have some say. But
I'm sure we'll return to the activities of SciAm later in the discussion.
Good. We'll return.
Thank you, Susie. So our third panelist is Brendan Hassett, who is also an organizer of this meeting. Brendan is the director of the Institute for Computational and Experimental Research in Mathematics, ICERM, as well as a professor at Brown University. His research interests include algebraic geometry and number theory. Brendan.
Thank you very much. So the Institute for Computational Experimental Research in Mathematics was founded in 2011 at Brown University. The founding director was Jill Pfeiffer. We rely on NSF, but also the Simons Foundation and Brown University and academic and individual sponsors to support our programs. So our programs are primarily driven by proposals from the community. And so we welcome ideas from all across the mathematical sciences community. So we aim to run programs that go beyond just the interests of Brown faculty, but really touch on all the mathematical sciences as it's done around the country and around the world. So our mission focuses on the interaction between computer experiment, algorithms, and progress in the mathematical sciences. We're interested in using computer experiments to try to learn what's happening in a mathematical system. We're excited about the prospect for machine-assisted proofs, computer-assisted proofs, and disseminating the ideas behind them. We encourage people that have theorems that can lead to algorithms to develop the algorithms and disseminate them. And we also encourage people to develop and share software that can help drive progress in the mathematical sciences and help disseminate important mathematical ideas and help people to visualize what's happening in complex mathematical systems. And so our mission is executed through programs of various kinds. Our largest programs are semester programs that run roughly contemporaneously with the Brown semester. So we recently had a program in discrete optimization. We've had programs in braids and computational and combinatorial algebraic geometry, in computer vision. And so these semester programs include postdoctoral fellows and long-term visitors. And there's also a number of embedded workshops that have larger groups collecting at ICERM. We also run a number of freestanding workshops, ranging from 2 to 3 day hot topics events to week-long topical workshops on all branches of pure and applied mathematics. And so we've had recent workshops on scientific machine learning, which is a good instance of how artificial intelligence is changing approaches to scientific computing and physical problems. We're proud to have hosted, and Heather, shout out to Heather, hosted a program last year in Lean for to encourage more members of the mathematical research community to participate in the Lean program. So that's something we're very proud of. We have quite a lot of programming related to computational number theory and arithmetic geometry, including the development of large databases that could be used for training purposes for AI algorithms. So we have a wide range of different kinds of activities. We also have small group collaborations that we host, and a summer program in undergraduate research running 8 weeks that just started a couple days ago. And so the distinctive aspects of how we operate is that we encourage participants not only to present the theorem, the thing that will appear in a prestigious mathematics research journal, but also to show the process of discovery, to indicate what software and what techniques went into the discovery, to communicate the whole range of mathematical scholarship other than just the end product of a theorem and written in formal traditional style. And so many of our programs, they involve coding, they involve tutorials that get people involved in using various techniques that are available to help drive mathematical research. And so we try to basically provide a public space where people can talk about all the things that mathematicians are doing, not just the end products of proofs, and also to discuss how computational tools can inform and inspire mathematical discovery. So part of what we do in order to achieve this mission is that we offer all of our long-term participants and many of our short-term participants access to scientific computing resources of various kinds. And we create sandboxes where people can take software they've developed and share it with other participants and try it out and show people how it works. So those are the main elements of what ISERM does. Part of our mission is to encourage interactions between computation and mathematical sciences research. And so we're really excited about what might come out of this initiative, and particularly the potential for artificial intelligence to change how mathematical research is done. Thanks, Heather.
Thank you, Brendan. And finally, so our final panelist is Dmitry Shlyakhtenko. So Dima is the director of the NSF Institute for Pure and Applied Mathematics, IPAM, and is professor of mathematics at UCLA. His research is on operator algebras and includes free probability theory, random matrix theory, as well as von Neumann algebras and L2 invariants. Dima.
Right, thank you so much. And it's a great pleasure to be a part of this meeting. IPAM is primarily an NSF-funded mathematics institute. We're located at UCLA, and we've been in operation since 2000. And the mission of IPAM is to create interdisciplinary research communities to use mathematical techniques and inspire new mathematical techniques in connection with real-life problems. So I'm actually right now at a retreat that we hold for at the end of some of our programs. So I'm not at UCLA right now, but at Lake Arrowhead. So I apologize if my internet connection is occasionally spotty. But just to give you an indication of the kinds of things that we currently have the end of the program that we've just hosted, which is about mathematical techniques and challenges brought about by exascale computing that is now in existence. We also have a group of people that are control theorists and traffic engineers and who have interest in autonomous vehicles, who are coming here for a reunion, and also people who are studying gravitational waves, which include everybody from people that do signal processing and machine learning associated with detections of these waves to theoreticians like people from numerical general relativity or numerical astrophysics that provide some of the data that is necessary for the signal processing people. So what's special about IPAM is that most of our programs involve groups of people that come from different subjects. So we always have some mathematics, but it's mathematics and more mathematics from a different side of math, or it's mathematics in a different discipline, such as the ones that I've listed above. Our major programs are long-term, 3 months long programs that start in what more or less corresponds to the fall and spring quarter at UCLA. We also run a bunch of standalone workshops, which are usually 4 or 5 days long. And we also have graduate summer schools which are aimed at graduate students and postdocs who are interested in learning about a specific subject or possibly moving into a particular subject, and a number of programs aimed at undergraduate students and graduate students having to do with industry-inspired research. So these are where students work on projects provided by industry partners. In terms of the connection with machine-assisted proofs, we're very intrigued about this. In fact, one of us past winter was on machine-assisted proofs, and it touched upon some of the subjects that were discussed in this conference. Here, I think the subject was more on AI, and so we had some connection with that as well during that workshop. And we're very interested because it sounds to me like this is kind of a situation where several groups of people working on similar subjects from different sides, be it people who are interested in formalization of mathematics or people who are interested in connections with AI, are working on something from different angles. And so we would really like to see the success of that approach and more integration and more discussion between people. And we've seen that a lot happening, throughout the recent months, both at the IPAM workshop and some other events that have happened. So we would really like to hope that there's more interaction and more unification among the various communities that are working on this subject. So I think I exhausted my time, so let's maybe move on to other things.
For sure. Well, thank you for landing on that note, because that was one of the first things I wanted to talk about. So all four of you and the organizations you represent already have existing frameworks for interdisciplinary work, existing frameworks for interacting with fellow societies, existing frameworks for bringing different groups of people together. I mean, AI is a special case of this interdisciplinary work, but it's something that you have all been thinking about for a long time. I think many of you can comment on this, but maybe I'll let Susie start. And can you give us a sense of what it looks like in practice to partner with different groups of people for SIAM?
So SIAM is member of some societies such as the Computing Research Association, right, which has as members some societies, but mostly academic departments and things at universities in the computer science. We are a member also of the American, so I'm going to get this wrong, AACC, which is related to control, and our members do work towards their proceedings and those conferences and things like that. We're certainly a member of reciprocal societies. We share conferences or prizes with ACM, which is computing machinery and things like that. We are a member with MAA, the Math Association of America, American Math Society, and American Statistical Society. We have a joint policy board in mathematics where we share some thoughts on science policy issues, and that's more US centric. But our members, as I've described before, are fluid from SIAM to other societies, right? We have engineers, petroleum engineers of all stripes and all these things. So all that information, all that collaboration comes in. They may do, we may run sessions at other societies or other organizations, conferences, and vice versa. So it's a very natural thing because of who our members are as well. So that's
an interesting point. Maybe Gunnar, if you're willing to jump in, how is the BMS partner, given that the members don't have those intrinsic links necessarily?
Yeah. So, so of course the links are stronger with allied disciplines. So the American Statistical Society and the Association for Symbolic Logic and SIAM. But the way that I have seen it work in the AMS, and I should say, for the most part, I've been an outsider to AMS. I'm in there now, so I don't have a full history of that in mind. But oftentimes it comes in supporting workshops of an interdisciplinary nature at some of the institutes. So, at MSRI and at the American Institute of Mathematics, encouraging mathematicians to go there, to attend those things. I think that's the largest point of it. Actually, I think we could benefit from more and moving out to slightly disciplines that are slightly further removed.
Brendan and Dima, both of you, I mean, the institutions that you run, I mean, have partnerships in place with other disciplines. Have there been any particular challenges in finding ways to build these connections?
Maybe I'll go first. So one thing that we've discovered is that when we have an interdisciplinary program, so often people from different disciplinary backgrounds engage with it differently. Mathematicians are quite happy to pick up and spend 3-4 weeks away from their home institution and immerse themselves in a community of other people. But many people working in applications, biologists, computer scientists, and certainly people working in industry and in government labs, they can only visit for shorter periods of time. And so we try to be intentional about creating environments where meaningful interactions can happen, but in a way that makes sense in the sort of the life rhythms of all the people involved. And so when we design a program, we'll often have short concentrated periods where we hopefully will have a large number of people coming at once from a target application area, and then longer periods of time where mathematicians and mathematical scientists can digest the things that they learn. One aspect of our programming is that most of the people that sort of apply to be in our programs, all of our programs have both invited participants and applicants. They're people that are already familiar with our model and our mission, and so often there'll be interested people in the mathematical sciences core disciplines that want to branch out and develop new connections, and they'll see a program at ISERM as an opportunity to make connections to people in the application areas that have some interest in engaging with mathematicians. So I think we just have to understand that there are cultural differences and try to design the processes so that everyone can get something meaningful out of their engagement with the Institute, even though it might be different things for different people.
So maybe I could just add one more observation, which is that oftentimes when you have groups of people that come together around a common problem, they all have their own insights, but they also have their own descriptions of the problem. So it's a bit like having, I don't know, manifold or something like this, and you have different charts that see different parts of the manifold, but they overlap, of course. But the coordinates are completely different, and the meanings of these coordinates are completely different. So what's very important is to get people adapt at kind of changing coordinates, to be able to say things in one language versus another language. Oftentimes what happens is that they start kind of observing that many of the things that they are doing in their own discipline are rediscoveries sometimes, or novel discoveries that are of relevance or have been prior to that of relevance to other disciplines. And so in some sense, it's both the fact that there's a lot of convergence in approaches between different disciplines, be it mathematicians or physicists or chemists that look at a particular problem. But on the other hand, it's kind of sad that there's a fair amount of duplication of effort, where the same kind of mathematics, let's say, gets discovered by different groups of people, and they aren't aware of it, and sometimes don't even want to be aware of it until they realize that there's some benefit to them. And so it's important to kind of bring out that benefit and break down some of the barriers that they face in that translation.
That's certainly a very interesting observation. You might enjoy, if you were not already there, the panel between Jeremy Avogat and Hussein Fawzi yesterday, talking precisely about their experiences trying to cross boundaries in this way. There were a lot of the points that you just mentioned discussed there as well. I want to switch gears a little bit and ask you to reflect, not necessarily as representatives of your organizations, but just in your capacities as distinguished mathematicians. Do you have anything perhaps to reflect on or add from what's happened in this workshop about what AI can do for mathematics? I think there's sort of the obvious thing, which is that it can help us prove more theorems faster. But I think it's also interesting to speculate and to hear what mathematicians themselves really want from this technology. Dima, maybe I'll get you to go first here.
All right, well, I was warned that this involves some speculation on camera, which is what I will be doing, so don't take it too seriously. But I was just struck by, you know, of course, the thing that right now everybody's talking about is things like ChatGPT, these generative pre-trained transformers and things like that. The early iteration of that technology came about from language models that immediately found a very interesting use, which is actually translation, right? I mean, Google Translate and things like this were based on ingesting lots of literature in different languages and pre-existing translations from different languages in building a fairly good way of translating things from one language to the other, which somewhat preserves meaning. So kind of very speculative, I'm wondering if it would be possible somehow, especially once a fair amount of mathematics gets formalized, to have this change of coordinates that I referred to somewhat automated. In other words, if I input what my definitions are, so definitions in this sense are kind of like variables, right? I mean, they are the things that you care about. So if you input your sets of definitions and what you care about in your corner of science or mathematics, can you have a paper translated into your worldview? And this translation does not even have to be all that precise and exact. I mean, if I'm a physicist looking for just a sense of what is this about, it would be fantastic if one could get that sense from a math paper that is impenetrable to me at first glance. So I think that might be a lower hanging fruit than being able to actually, you know, stipulate conjectures and propose formal proofs. Just the same way as writing novel text that looks interesting and human is much harder in principle than just taking existing text and rewriting it in the style of. And I want to mention one more thing, which is kind of perpendicular, which is sort of a fear in a sense. Mathematics has invested several centuries of notation and education in making sure that just about any scientist out there can read certain type of mathematics. And I think it's important that whatever we do in terms of how we present mathematics of the future, be it formalized or whatever, that we don't lose that connection. That is, it has to stay readable, or there should be bridges that allow it to remain readable and relevant to application areas which are not people who are fully trained in mathematics, but have kind of the beginnings of that program.
Thank you. I'll say there's this famous book, General Relativity for Mathematicians, which is going in the other direction from what you're describing, taking an area of physics and trying to replace it by theorems so that mathematicians can get a sense of what the hard parts are. And I think, if I remember correctly, that the authors say in the introduction that they have come to the conclusion that this kind of endeavor is really just impossible, despite having produced a book at the end of it. So certainly more tools are needed here. Would someone else, I don't necessarily want to pick on anyone, like to add to what Dima said, either to object or to add?
I'd love to jump in here if I can.
Please do.
Yeah. So I'm very sympathetic. I like the idea of doing automated theorem proving and verification of proofs and so on. But I think it's important to recognize that mathematical reasoning, which is what we're talking about here, is not exclusively theorems and proofs. There are many other aspects of mathematical reasoning. One is just simply, experimentation and reasoning that way. Another thing that I would mention, though, is the notion of idealized models. You have a complex phenomenon, but you have an understandable an understandable model that you can develop. It won't be perfectly accurate. In fact, it might not be quantitatively very accurate at all, but it might indicate the behavior that's going to happen. So think here of mathematical economics, for example, where I think one all knows that many economic models don't do terribly well at actually predicting numerically what's going on. But on the other hand, it's giving a qualitative idea of how things behave. So I'll say I have a personal experience in this regard. So, well, let me say, so what I would love to see is, artificial intelligence now, which is, an enormous field full of things that are doing lots of brilliant things. But I think it's also safe to say that it's not very well understood. That is to say, we know how it works, we'll understand better and so on. But an idea would be to try to develop idealized models, to get mathematicians involved in trying to build idealized models. I have personal experience in this regard where we did some work on machine learning on images, learned a certain kind of feature generation, and because we understood that feature generation, we're able to make the leap to what the same thing should be for video. And that's sort of thing that doesn't happen when you just do things empirically. But if you have some sort of mental model of what's going on, you can make those things and shortcut a lot of research. So I would love to see more mathematicians involved in all stages of this, in the formulation stage of problems. I think that's, we tend to want, and I'm speaking here of, myself 30 years ago, we tend to want someone to give us the problem. You formulate the problem. Please hand it to me, the mathematician, and I can, take that step and prove it. And I just think that's extremely inefficient. So I want to argue for and would encourage, mathematicians, and this is really on us, so to speak, that everybody should be at least aware of what problems are available out there, so that you can see if something in the pure math that you're doing can actually you can guess that it might have an effect. And anyway, I think that, artificial intelligence is a place now where there should be room for a lot of these, mental models, and in particular because of the issues around it. So, there's a whole area of explainable AI that's developing, and it's important to understand it's important to understand what's going on inside it. But, it can lead to things like smaller models. If you have smaller models that maybe are cheaper to run, because the big models are obviously very expensive computationally. Generalizability is another one where, oftentimes you train on a data set, say of digits, and you try to evaluate it on another data set of digits, and you find that you don't get any utility at all out of it. So one would want to have generalizable models, and hopefully also perhaps, cut down on the expense. There's a lot of opportunities for understanding and optimization going on in there. And I'd love to see mathematicians involved, but it's going to involve, as we've seen, stretch on their parts to sort of incorporate more than just the straight pure math that we're doing. So, okay, I'll stop there.
Thank you, Gunnar. On that point, perhaps for people who haven't caught the whole workshop, I'll mention a few other places where this sort of thing has been discussed in the last few days. Jordi Williamson in his opening talk, and also the Mathematical Foundations of Deep Learning talk. I think both mentioned somehow that there are really great mathematical problems, pure mathematical problems out there for us if we know where to look in these new and developing fields.
But I think it involves a stretch for us. We can't sit and hope that people doing AI are going to formulate it for us so that we can do it with our math. We have to get out there and be a little bit external facing and, do the work to find out what it is they're doing.
Absolutely. We need to reach into the massive clay and form the problems ourselves.
Right. So with regards to your question, and it's been mentioned once or twice, but since you want to know what's interesting or exciting for us, I saw some of Rebecca Willett's presentation, right? She had a slide titled, "Can we learn governing equations from data?" Right? And we talked about experimenting. So I myself, come up with new theorems by computational experiments, which was me pressing a button, just randomly generating parameters. And then you're like, wait a minute, what's going on here? I'm seeing this thing pop up every now and then. What's going on with this, and figuring out there's a theorem there and digging more deeply. But yeah, we have so many things. If we're looking at climate science, extreme predictions of extreme things that are happening in the weather or in climate, we have so much new mathematics that we need to understand these things. And I think AI and machine learning and all these things are very much a part of this. So I'm not talking about theorem proving, right? So I know that's a major thrust for this workshop, but as far as mathematics writ broadly, I think I love this part about the AI and the machine learning informing what we're doing and giving us insights that we can't see. Data could be too massive, but that will inform us, right? It has some sort of weird sort of microscope or something that can see more deeply than we can. So.
I like that a lot. I actually, if I may, so one special case of the question of, forming feelings and impressions from huge amounts of data. I think Dima raised this in the preliminary discussions for the workshop. One place where there's just too much information now is the mathematical literature itself. I think that Dima had some thoughts that perhaps a special case could be just helping us sort through the mathematical literature.
One thing that I think is important from my perspective as an institute director is a lot of what institutes do is create communities of people who are interested in problems or interested in techniques and helping to create environments where the whole can be more than the sum of the parts. Running counter to this vision of someone working alone in their attic trying to prove a theorem that was handed down by a famous person, and make their mark through, a paper in one of 3 or 4 journals. And I think that a lot of the collaboration styles that one sees in both proof assistance like Lean, but also in some of the machine learning projects require more complicated collaborative structures than mathematicians have traditionally used. One of the things that MathSciNet shows over time is that the size of collaborations and leading to papers has grown, and I think that we're at a sort of an inflection point where we'll have much more complex groups of people leading mathematical discovery, both because of the nature of these proof assistants, but also because to make progress in machine learning-oriented mathematics, you need people who can both design conjectures and see patterns, but also people who can get the software to do the things that you need. You need complementary skills from different disciplinary and backgrounds. And so I think that this is something where institutes and organizations can play a big role, helping mathematicians find those collaborators and find those groups so that they can be productive in these new kinds of research problems.
And this may have come up earlier, Brendan, but the hope is as our world of mathematics and our world of collaboration evolves, as you said, the groups are getting larger. Hopefully, let's look at those in the academy, right? Can look at that in the right way and not saying, well, no, we're your sole author papers, right? We're not regarding that as proper scholarship. And I think this came up somehow, maybe not this exact question, but we can hope that the community evolves to appreciate that for what it is in these new paradigms. Yeah, it's very important for that to happen.
Maybe it's good to mention, I mean, so the first detection of gravitational waves by LIGO, it's a paper with, I think, around 1,000 authors. And then, so this is the 2 black holes, a collision between 2 black holes. The first detection of 2 neutron star collision, I think it's around 4,000 papers because it involves not just the LIGO people, but also people that are with computational sides of things and astrophysics and so forth. I mean, this is the scale of collaboration that we're not used to in mathematics, but this is happening more and more elsewhere. And of course, it creates all kinds of interesting questions that I think were touched upon briefly in the previous panel about how we recognize that in terms of career advancement and so forth, right? I mean, it's so easy to count single author papers. It's so easy to count citations to single author papers and H indices and all that. All of that becomes much more complex once you have these massive collaborations. And so perhaps we should move away from some of the metrics we're used to. And I think in mathematics, actually, we should take pride in always, at least, the institute I come from, we always dealt with promotions and hirings and so forth in a very holistic way where, we understand there are differences between areas and things like that. And I think this is what probably needs to be done a lot. And perhaps there should be some advocacy on behalf of professional societies in that respect to make sure that, efforts such as proof assistance and formalization of mathematics get the proper recognition that they deserve.
Yeah. Perhaps, I think this is a great place to start talking, as you said, about the roles of the professional societies in particular. One of the things that the professional societies provide for mathematicians that you see every day as a working mathematician is these resources that Gunnar mentioned, for example, MathSciNet and MathJobs, and also other things like I think there's a general guide for mathematics departments giving the context of mathematical research that departments can use in advocating to their universities about promotion and tenure. Maybe there are all kinds of new shared resources that can be put together, perhaps with the help of the societies or with the institutes that were not relevant in the past. The development of computational databases of enormous scale that need to be shared in some central hosting, the development of data sets for training artificial intelligence, the development of formalized mathematics libraries. Perhaps there are new kinds of shared resources and new frameworks needed there.
Well, I wonder, of course, you mentioned MathSciNet. Can one imagine an AI SciNet or that where one can search more effectively than going just through Google Scholar? Google Scholar is fine, but if I'm looking for a math paper, I'll definitely go to MathSciNet because I'll know I'll find it much more readily and so on. And I just wonder here if there's room for a specialized resource like that. Maybe AI itself is actually too broad. Maybe there need to be multiple such, theory of AI and so on. But resources, specialized databases, and maybe slightly on a perpendicular here. I feel like within mathematics, there's a need to move to, or at least that there should exist publication models that aren't quite like the ones we have in mathematics. One of the characteristics of it is that it's extremely slow, and other sciences, it's not that way. Now, that's because, in part, you're evaluating a proof for correctness and so on. But maybe for the more experimental mathematics, one could hope to have a publishing model more like the other sciences.
What does that mean to you, Gunnar? Because, you just said a final sentence and say more about that, because we do have to review things, right? It does have to go through scrutiny. That's different. The papers are different lengths. And, I've been to many editorial board meetings with our various journals here, and it's much faster than it was when I submitted my first paper, but it takes work. So, but tell me, you said something, your very last sentence said something about experiments or something?
Well, yeah. So in other words, I think, when you have the proof of Fermat's last theorem, then has to go through all the 100 pages of that, and maybe it's just not possible to speed that up very much. On the other hand, when you're doing experimental things, experimental mathematics, maybe then it's possible to emulate the models that occur in biology and physics a little bit more. I don't claim to know how to do that, but I just feel like the refereeing thing is a huge bottleneck to us, to mathematicians getting involved with AI. Yeah,
I'd like to address something that was in this conversation. So, as an experiment, ISERM is running a workshop on the L functions and modular forms database, and we basically offered people the opportunity to submit manuscripts, developing algorithms and showing how these resources could be used to discover new results and new theorems, and reviewed them like a computer science conference did. And so obviously we're not taking away any papers from the Journal of the AMS through this process. It's a different kind of scholarly output, but I think it's also quite valuable to have an outlet where people who do the work of developing the databases and finding unusual examples where this work can be disseminated quickly to a wide audience. And so I think there may be other branches of the pure mathematics enterprise where we can take a page from the computer scientists and, at least for some of our output, use models like this. And again, this is not how you're going to publish a proof of the next Fermat's last theorem, but I think it can be important in helping to build communities and build expertise in areas where data and algorithms are a driving force.
Perhaps I'll mention just the counterpoint that it is, possible with some of these technologies that we'll be able to speed up the review process, 10 or 20 years in the future by offering computerized proofs at the same time as the articles themselves. Already this has happened a few times, notably a recent work of Thomas Bloom on a density conjecture about unit fractions came submitted to the journal together with a formalized proof put together by him and by Bhavik Mehta. And, obviously this is happening only in special cases now, but it may be something that happens more and more in the future, taking some burden away from referees. So perhaps we can talk more. So we've spoken about journals. Perhaps there are other kinds of core activities that your institutions and your societies are involved with. So conferences and semester programs and the publishing of books and prizes. And I think it was Brendan who already spoke about, for example, the kinds of changes that were needed to the semester program model to better support the needs of people from other disciplines. Does anyone else want to share some thoughts on how other core activities of your societies might adapt as they bring in broader groups of people?
Well, I just think that, and we're seeing it will happen, and it is happening. But the ability to run virtual conferences, should mean that we can run many more conferences and get much more interaction. Not to take away from the value of in-person interaction, which is really important. But my feeling has often been that when sending 50 Americans on flights over to Europe for conferences, maybe one should do that more sparingly and have more virtual ones. And that might be a little controversial, but my feeling is that you get 90% or 80% out of the virtual ones, and so of what you would get from an in-person meeting. So I'm curious what everyone thinks about that.
Well, I can tell you that I think there was some excitement about Zoom conferences and things like that early on in the pandemic. I think now at least all the people I speak to are very heavily in the Zoom fatigue era. In terms of being, what you said about 90%, I mean, my personal feeling is that there are different styles of conferences. There are some conferences that can be effectively replaced by YouTube recordings where you just listen to some talks, and these can be even run asynchronously. And some of the talks, some of the explanations that exist out there like the Math Institutes have a video library that's operated jointly, and some of the things there are gems and they're fantastic. But there is something special to being able to pull a person aside afterwards and ask your stupid question in your own way, and get that person to react to it after several attempts. And this is something that I have not been able to ever see reproduced online. And if you want an experiment, this just came to me at a moment where I was at my first physical conference after COVID, where I was sitting with some co-authors and we were talking about something. And I just realized that we spent about a minute in complete silence. And I just welcome you to experiment of trying to be silent in Zoom for a minute. There'll be complete panic, first of all. And secondly, this is just not a medium that's conducive to this kind of stuff, where you just, think and meditate, and then you say something that's sort of nonsense, and then somebody reacts to it and corrects it, and it slowly converges to something that has meaning. So I think there are just different styles of communication, and some can indeed be well imitated in Zoom. And I agree that flying internationally for a 1-hour talk where you come to your talk and leave is the height of stupidity. But going to some activities where you do have a lot of interactions besides formal talks, I think is absolutely essential. And this is something that was very much missed during the pandemic.
So one major thing, as I said in my introduction, that SIAM does is put on conferences, right? In 1 month alone, I'm just like, I'm almost exhausted thinking of it. And I've canceled one conference I was supposed to be headed to this week, and which has allowed me to be here for this. But I was surprised by your 90%. So you must have a very good discipline and personality. There's no way, that's the highest percentage I've heard. There's no way that right? So there's a range. Some people are like, oh, this is just great. I can do this at home. And then some people are like, well, I have the computer open and I have 100 emails. So I'll try and do both, which means, you know what that means. So SIAM, of course, and AMS, et cetera, well practiced in-person meetings. We did completely virtual meetings. We did fully synchronous streaming last year, for most of last year. Staff, conference goers, I think, are much, much happier in person. Dimitri Dimas already said some of this. It's not just delivering or hearing the one talk. And I mean, we heard there's a lot of confusion about that when people looked at the pricing of conference. No, it's not just for your one talk. It's all the other stuff. It's that community. It's that conversation. It's just priceless. And once you go back, you're like, oh my gosh, this, sometimes you don't realize what you're missing completely until you're back in it. And all these conversations and seeing people talking, whether they're talking about math, whether they're talking about family, whatever, but making that connection that sticks. And I think it was, am I getting the name right? Ursula, who spoke on the first day. And she, Ursula Martin. And I remember when she talked about collaborations. If you have 1, 2, 3 meetings, it's not working, it's just not working. And it's about chemistry, right? And one way to really fully explore that chemistry is, you don't have to, but physically being at the same place and seeing that working out. And I've also heard people talk to me about their students, right? The students having lost so much. They know what it's like to talk to each other at the university when we were kind of limited and shut down at the height of the pandemic, but going out and meeting with other people and collaborating, this is important. And I'm saying all this with the full recognition that we do want to be careful of what sort of footprint we're leaving and all these sorts of things. But yes, if you're going and being selective for a full experience, then it's in some measure, hopefully it's worth it.
Thank you. Let me pick up that point about students because it relates to a question that was asked on the live stream for the conference. Someone wanted to know your thoughts about the younger generation and how they should learn to interact with these new technologies. Does the way we educate our students need to change, and how young is too young?
How young is too young to get involved in AI, or just?
I think that was the question. How young do we want to start involving AI or machine techniques in the mathematics that we teach to students?
What is the issue? Is the concern? I know you didn't write the question, Heather, but is the concern circumventing the whole process of doing proofs on one's own? To me, if someone's interested in learning it, why not teach it? Why not have a summer school? Why not have a tutorial before a conference why not run an REU program?
It certainly sounds like you're in favor. Let me try to
but maybe somebody else knows the nuance about this that I'm not recognizing.
So maybe I can just comment on one thing. We have this undergraduate program at IPAM, and so we evaluate candidates. Of course, it's somewhat self-selected for people who are more applied math minded. But over the 6-7 years that I've been looking at these applications, there is a significant change in terms of the typical undergraduate experience from people that have just sort of dabbed here and there in some amount of scientific computation to people that have, generally speaking, have done substantial work on projects having to do with AI, deep learning, and all that kind of stuff. So I think that, as far as AI is happening, I think this is just happening. Part of it is universities adapting their curriculum to this, and part of it is just natural that, kids, they have a computer with a GPU, so why not try this? Now, in terms of the other question of which point should one get people on lean, and should they be weaned off lean at some point, I don't know. What I wanted to point out, this one point I made earlier, is that whatever we do, we have to make certain that mathematics stays relevant and connected to other sciences. So therefore, it's important that whatever language is adapted, it's sort of taught early enough in, say, undergraduate or even high school careers, so that people can sort of relate to it. They don't have to be experts in it, but at least they should be able to read it. And I think that has happened a lot with computer science over the last 20, 25 years, maybe 30 years, I don't know. But it has to probably happen more with computational mathematics.
I think one challenge in pure mathematics is that it's possible to teach something like group theory using a very formal, very standard method, and it was the same course as it was 50 years ago. And it may, there's the formalism of the pedagogy. It has advantages for mathematicians that anyone can teach any course. But if I'm going to introduce lots of computational examples and access to database and teach people how to use software, it requires a much different level of engagement from a pedagogical perspective, and it makes the courses, it's not, you just can't hand it off to a postdoc 3 months out of graduate school and say, teach this. It requires a range of skills beyond just the formal understanding of how the theorems work together. And so I think that this is probably a challenge, at least what I see in pure mathematics, to implementing some of these new perspectives for understanding into the curriculum. And so this is something I think we as mathematical scientists have to reflect on, how we can provide enough flexibility in how we teach so that these new things can seep into the curriculum at an early stage. It doesn't need to be all AI or all formal things, but people can at least get some exposure to how you can use these as tools to generate understanding.
And unless there's new data out there, I don't think the US is yet in the situation where we're producing too many students who are STEM capable. I don't know if anyone's complained that the US workforce is too STEM capable. We have too many people, highly competent in machine learning, data science, and AI, and all these sorts of things, right? So we may still want people to be able to do things, and let me call it a traditional way, and that's absolutely fine. But I know personally, I'm not yet at the stage where I'm saying we should not be teaching people more about X, Y, Z. I don't think we're there yet. There's lots of work to be done, lots of employment to be had, lots of technology and economic advancement, and all these sorts of things, and just general knowledge that we had.
So I just want to make a strange point about the math education part of it. It's very interesting that because of the way computers ingest mathematics mainly, mathematics is increasingly algebraized. I don't know, it becomes more algebraic. There's a lot less geometric argument, for example, that tends to happen certainly at more elementary level. And I think there's some research that shows that there are kids that are naturally more happy with this kind of thing, and they're happy to do it. Then there are some kids that are not, and they might be very well adapted to geometric proofs and things of that nature. And so this is something that could be something that should be looked at in the context of injecting even more algebra, so to speak, into the system. So there was some discussion of somehow how to formalize geometric proofs and something like this. And if something can be done in that direction, that could be wonderful, because it might reach out to an untapped segment of the population who naturally is very good at this and then kind of gets discouraged from doing mathematics just because of facing too much algebra early on.
Let's also experience a conversation that obviously could go on for a long time, but we need to pass on to George and Ellenberg for concluding remarks. Let me just say, I think, maybe the conclusion is, as you all have said, we just need more. We don't need to take anything away from our existing approaches. We just need new additional approaches. And I think that is something we all hope to achieve. Thank you all, Gunnar, Suzanne, Brendan, and Dimitri, for your contributions to this panel. Over to you, Jordan, for the concluding remarks.
Okay. Hi, everybody. Am I on the live stream right now? Fantastic. Okay. Well, I've been given the task of summarizing what's happening in this field and what's happened over the last 3 days. This is a very fast-moving area, so it is pretty challenging a task, right? It's a field that sort of somehow you feel like it's changing even as you try to summarize it. Let me just start by thanking everybody for coming. I'm told we had more than 2,000 people register for this workshop. I'm not sure how many people are watching right now, so it's great to see sort of so much interest in a field that I think all of us here are really excited about. And thanks, of course, to our speakers for preparing really wonderful presentations on very short notice. We put this together very fast, thanks to the great people at NASM. And who participated in such interesting discussions, including the one I feel a little bit guilty for just cutting short to sort of say my piece at the end. I mean, just listening to what we heard over these past 3 days, I mean, we're sort of in a moment of discourse where everyone seems to be compelled to have a take on AI and where it's going. And it's quite refreshing in that context to have this conversation that's grounded in things that people have actually done and are actually doing, right? It sort of feels much more factual and much more real. What are some of the takeaways? I think we've seen that this field is incredibly multifarious. It's not just one thing. We've talked about, just to pick a few, like reinforcement learning to generate new examples, formal languages in which we can codify mathematical reasoning or some kinds of mathematical reasoning in machine processable form. And then again, we started to sort of speculate about machine architectures that can capture the non-proof parts of mathematical reasoning, which I think all the working mathematicians in the room and on the screen know is kind of a pretty critical part of what we do as mathematicians. Let me say too, I'm just sort of cataloging themes that have come back again and again. This idea that it is going to be a two-way process, even though the title of this workshop, AI assisting mathematical research, sounds a little bit one-directional. I think everything we heard today indicates just the opposite. It's quite heartening, actually, that I think there's universal agreement that communication between groups of researchers who speak different languages is of critical importance, and neither is to be subordinate to the other. So much I could say. I really liked Adam Topaz's idea that our experience as mathematicians of knowing what is a good definition, of sort of chunking concepts into useful definitions, can be useful for people who are trying to understand how to engineer prompts. And also, I sort of liked this metaphor of translation. There's a lot of metaphors in this workshop, but one of the central ones was this metaphor of translation that really reverberated through lots of stuff that we heard. I liked it. François Charton talked about thinking of the simplification of an algebraic expression by a machine as a form of machine translation, right? Sort of like translating a complex algebraic expression into a simpler one. Maybe another metaphor that I found quite notable in this respect was what Becca Willett said when she said investing in applied machine learning without understanding mathematical foundations is like investing in healthcare without understanding biology, which is a pretty interesting metaphor for the relationship between the two fields, especially because, I mean, let's face it, we do invest a lot in healthcare without understanding biology, right? We mostly don't understand biology, and there is a lot of stuff that we do in healthcare that kind of works, and we don't know why. And those two fields work in a really interesting iterative interplay where, on the one hand, applied work will sort of like leap ahead and the biology sort of tries to figure out why what's working is working. Whereas at the same time, foundational biology, basic science is there to sort of help direct the applied work in what is likely to be a more productive direction. And I think that's a very interesting metaphor that I had never thought of for the relationship between the two fields that are represented here. Let me come back to this idea of translation that was mentioned in François' talk. I want to come back to it because when we look at output that's generated by a machine, whether that's an example of a graph, it's an Adam Wagner's talk, or a piece of code produced by a large language model, or a formal proof outputted by a machine that's trying to find that. We're looking at writing in a language that we only dimly understand. Maybe that's the way I would try to make that translation metaphor work. Of course, we want to be able to interpret what it is that we're reading, but not just that, not just trying to understand what information is being conveyed, but trying to learn something about the language it's in. And that on the one hand can feel very new, but for mathematicians, I think it's also not new. I think that actually in some ways has always been the experience of mathematicians as we encounter, the mathematical phenomena we experience out in the mathematical world. At first they seem strange and exotic, and then they start to become familiar. And finally, the last step is that they become legible. we start to understand what's actually under them and what structures generate them. I got to give my favorite quote from Andre Weil, who in his famous article about the 3 columns, he writes about these kind of phenomena of analogies between number fields and function fields. He writes about these mathematical facts. These texts are the only source of knowledge about the languages in which they are written. In each column, we understand only fragments. And actually, I put in my notes that I wanted to give that quote, and then as it happens, Adam Topaz pointed out in his talk, he gave this analogy as this very analogy that we associate with Weil as an example of something he could not imagine a large language model generating. So we'll see, but it is a famous analogy. I mean, but the good news is that unlike in Weil's world, where the texts in that language we have access to are very sparse and are hard won, we can generate lots of texts very fast. And so I think there's a lot of hope that these new languages, maybe we can learn to read and understand them faster. I think we saw again and again in these talks, we saw, just to mention a couple, as in Javier Gomez-Serrano's talk on physically informed neural networks, and again, Adam Wagner's talk about counterexamples in graph theory, that these architectures that we're talking about, they can serve as, I guess, what I would call a rapid and eccentric exploration mechanism, right? Rapid in the sense that we can run it really fast and it can explore a lot and sort of generate lots of examples, and eccentric in that it's clearly doing something different than we might do by ourselves, which is where a lot of the value comes from. Can I go back to this Weil quote for 1 second? He says, we understand only fragments. And this word understand is also one that we heard again and again. It's kind of notable, I think, that we say ML, we say machine learning, we say AI, we're comfortable with saying artificial intelligence. We don't ever say AU, right? We don't talk about artificial understanding at this time. For the moment, I think this goal of understanding is something that we associate with us. And, maybe for the moment, now I'm sort of speaking for myself, somehow I've been put in this position of having the last word. Let me put my cards on the table as a mathematician and say that human understanding, growing, enlarging, and deepening human understanding is primarily what I'm interested in as a mathematician, right? And I think most mathematicians would say that. In this respect, there was an interesting question, a question in the Slido that I think was not actually asked in the talk. Maybe it was like too hot for the talk, but I'm going to just put it up there. I don't know who asked this question, but somebody said, what do you think about the role of mathematicians' intuition? Is the goal to entirely get rid of informal mathematical reasoning? I guess, given Alex's talk, I think we should actually call this scenario Kontorovich's nightmare. That can be like the new name of this scenario where human intuition is completely supplanted. Is the goal to entirely get rid of informal mathematical reasoning? Well, one thing we should do is answer that question with a question. Whose goal? I mean, that there are different people in the room with different goals, I think is part of the charm of this subject. And again, let me sort of be a mathematician again, speaking to other mathematicians, and say that working closely with engineers and computer scientists and machine learning practitioners, both people at Wisconsin, like Becca Willett, who used to be with us, who we miss, and Hussein Fawzi, that has been a tremendously enlarging and enriching intellectual experience for me. And I would, for real, recommend it to any pure mathematician. It's very invigorating to have that feeling of two people working together who have goals that are allied, but which are not identical to each other. I really liked what Moshe Vardi said in this respect on the first day. He said, if you're talking to someone and you're not authentically open to changing what it is that you're doing, you're not really talking to someone. That's a high bar for conversation, right? But I think it's a bar that we've been trying to meet in this workshop, and a lot of people have shown that they're successfully meeting. And I think that can be aspirational for us. That being said, to come back to the provocative question, I actually don't think it's anyone's goal in this room, or maybe anywhere, to get rid of informal human mathematical reasoning. I said that as a mathematician, I sort of put human understanding of things first as the goal of mathematicians, but this drive to understand, I don't actually think that distinguishes mathematicians from machine learning researchers and practitioners, in my experience. Now, they may be interested in human understanding of different things, than we are. For instance, a key question, right, is understanding why a machine learning system is doing what it's doing. This is the so-called problem of interpretability. This came up in Hussein Fawzi's talk. And I do think one thing that this domain of problems has to offer machine learning is it's a beautiful test case for interpretability in machine learning. In other words, like, can we actually understand what the machine is doing and why it makes the choices it makes? Why is it a good test case? I think one, because mathematics is a very old field in which there's some kind of consensus about what counts as insight. I think the examples of what interpretable machine learning would mean, I actually went to like a 3-week workshop about this at the Simons Institute last summer. And literally the first words of the first talk were one researcher saying, what the hell are we even doing? Right? That's the status of that field. Even the questions are not very clear. And I think that when you try to do interpretable machine learning in the sense of why did this machine deny this person a loan? Okay, you're already in a very hotly contested area where there's not going to be consensus about what the right answer is or what the answer could or should be. I think in some sense, math is a very good arena for trying to understand about something like what even could we mean by interpretability, because we sort of have some kind of agreement about what we mean by understanding, or at least we know it when we see it. So let me kind of sum up. I mean, since, as I said, for some reason, the National Academy has given me the last word. Let me confess that I am temperamentally an incrementalist. And I think the most likely future is always one that resembles the past in a lot of its aspects. And again, that was something I was going to say, and then Brigitte Pientka gave a very nice Santayana quote this morning, reminding us that looking at the past is the best way to understand what the future is going to look like. So I just want to emphasize that machine reasoning has been assisting mathematicians for a long time. That did not start this year or 5 years ago. Not by getting rid of anything, but rather by recategorizing certain tasks as computation instead of mathematics, freeing human mathematicians up to move faster and go deeper. Sometimes I kind of like to tweak people a little bit by saying the impact of AI on mathematical practice, it could be completely revolutionary, like that of computer algebra systems like Maple or Magma or LaTeX. And then people are like, what? Like LaTeX? But of course, those things actually have been immensely transformative of mathematical analysis, of mathematical practice and mathematical dissemination. So in some sense, everything we're doing is new, but it's also not new. It's new in a way that rhymes with things that have happened in the past. So yeah, this theme of the workshop, I guess, translation, exploration, and understanding. And my hope here, my optimistic takeaway, is that despite the barriers that we talked about in the session, the power relations between different groups, the lack of a structure for academic rewards, what role institutions can play that we just talked about, is that these goals, translation, exploration, and understanding, can be, if not mastered, at least developed in the service of something I think we can hope to call a little bit more than assistance, that maybe we can call it, if I can sort of suggest the title for the next workshop, collaboration. Okay, and I'm going to stop there. Thank you guys so much.
Thank you. Thank you very much, Jordan, for this very nice summary of the workshop. I think we are very fast arriving to the end of all the presentations of this wonderful 3 days that we had. As a last and a goodbye, I would like to say that what we are discussing today is not necessarily new. There is people that have been concerned with artificial intelligence for quite some time. So actually, I found a video from the MIT archives. The video is from 1963. Maybe some of you that are as older as I would recognize the presenter. It was a series about artificial intelligence at the time. And if I can share my screen, I would like to show you this particular video for a moment. Let me see. I can. So here it is.
Even the scientists argue that.
I go again.
Can machines really think? Even the scientists argue that. I don't believe that we can say yet that machines do think. I have a basic question which I always ask, and that is, are these producing anything really new? Until I see a machine producing genuinely new things, I will not agree that machines think.
I confidently expect that within a matter of 10 or 15 years, something will emerge from the laboratories which is not too far from the robot of science fiction fame.
Okay, perhaps the last person that you saw there, this was, I think, Claude Shannon of information theory. Closing words, I don't have more to say again than what Jordan said. I think what is exciting about artificial intelligence is that we have people from different walks of life coming together and discussing. It was wonderful to see computer scientists and mathematicians exchanging ideas. It was a lot of fireworks today that we will take us time to absorb. There will be another workshop with physical presence. It will happen sometime in late August, beginning of September. The proceedings will be available from this workshop. And I have nothing else to add here. I want to thank you for your attention and for being part of this conversation. And we are looking all forward to the next steps. Thank you very much. Goodbye.